live. Um, and I'm in the Twitch studio thing. There should be a way to see if anyone's in here. Um, I imagine. Okay. Can I mute this? Good. Super weird. Okay, I'm just gonna share on social links. Okay, let's share with the homies. Share with the homies. What channel should this go in? Cool. Cool. We post on Facebook. It's my first time posting in ages on here. Let's go on LinkedIn. I think this is how this works, right? You're supposed to blast your link. Okay, so on LinkedIn, you you have to add spaces, right, for it to count. So I'm gonna go like this, space, proper spacing, and we should add a clap at the end because it's LinkedIn. Can you even add emojis? Gosh, okay, hashtag, fine, streaming. Boom. Oh, nailed it. I have no clue who's in here and how to tell, but I think we're doing this now. It's kind of daunting, to be completely honest. I thought they would have got their UX a little bit better, but you know. Let me try messaging myself. Testing. I'm gonna try to do some recursion quick, see if I can hear myself. All right. Cool. This works. All right. Would I want to hear myself in the video? All right. Would I want to hear myself in the video? Nice. Okay, we got a ping back of about 4 seconds. That's all right. It's not like, it's nothing to brag about, but it'll do. Anyway, theme of this, why am I doing this? Why am I on a stream this fine Sunday morning? Well, I realized I wanted to do it for quite a while. And typically in life, if you want to do something, I think it's a good idea to just do it. And it was just frankly annoying me that like I hadn't been doing this. Like it doesn't take a lot of time. And I think there's two problems. So first, I don't jump into stuff enough. I think it's easy to think about things and then be like, that's crazy. I don't understand how this thing works. And then you just like don't dive in. And secondly, it takes forever to share something because you're like, well, I don't want to look dumb on camera. I don't want to do something stupid. And so I figured a really good way to force myself out of my comfort zone, just like as a developer, was to like live stream me doing stuff that I've never done before, that I have like basically no understanding of. So like maybe on paper people expect me to know this, but these are like areas where I'm probably below average relative to my like fancy titles or whatever. So how do I even drink this? Yeah, that's the point. And I don't know, maybe it'll get other people hyped to build cool stuff. I think the world would be better if people built cool shit, and like the more people that hack and explore their interests, the more rockets and like cures for drugs and poems and songs we would have. So cool. My headset just said mute on, so let me check it. Okay, this is one more test. Cool. My headset just said mute on, so let me check it. Cool, we're good. All right, so big thing on my mind that I haven't known about for a long time is how the internet works. And like, I think my level of knowledge on it relative to the amount I use it is too low. So I'm gonna try and build it, and I don't really know what that means yet. Like I kind of have a jumble of like stuff in my head. I know what the internet means, like IP and TCP and HTTP and FTP and SMTP and protocols, and I know that you can like send data across the air and it gets places, and that's super cool. But I would like love to understand actually more fundamentally like how it works from first principles. And I think the best way to do that is to build it. So I'm just gonna like jump in. I have no clue where this is going, but like let's just do it. All right. And I don't know how long I'm gonna stream. I'm kind of just like right now. I think I'm a little bit nervous because I haven't done this before, but I'm sure once I get into the flow, I'll have cat ears and you know, all the Twitch stuff. Okay, well, maybe I'll step back and like look at how I think the internet works from first principles, like my understanding, and then we'll refine it. Because I think the first step here is going to be so it's going to be like two things: figuring out like what I know, and then like scoping it out. Because like obviously we can't just go build a data center today. We got to start from somewhere. So let's do that. So I think in my simplest understanding, the internet is when you got a computer. You got that, and this computer is connected to another computer, and then it's going through this thing in the sky called the internet. That's, I think, the most fundamental reduction of like what's going on. Like I don't even know what's going through the sky. Honestly, I don't. I don't think it is, because like Ethernet and all these like wires and shit. I don't like, so even that baseline understanding of like what people think the internet is, I think is wrong. Like we call it the cloud, but is it really going through the cloud? No, I don't think so. And like which way is it all going, right? Like you're downloading stuff. Sometimes this computer could be uploading stuff and downloading stuff. So we got like bi-directional stuff being sent back and forth. Let's call this computer 2. So like, I think a couple of things here that I need to understand is, okay, like out here in internet land, there's a lot of stuff going on. There's like, I know there's this concept of like, let me see, to another computer. That's the fundamental, that's the internet. Computer sending data to another computer across the world. Or not even across the world, it's just data being sent to another computer. Let's see if I like understand that. Internet. Yeah, okay, cool. So there's this thing like TCP and IP, there's those fancy words. So let's just kind of make a word cloud. We got like TCP, we got IP, we got, you see here, I don't know if you guys can see this actually. I've got this obnoxious pane screen thing of me in it. don't know why that's necessary, Twitch, but okay, we got TCP/IP, we got routers, we got data centers. We've got, what else? How do I remove these like icons too? I'm just realizing Twitch has all these previews, like at least from what I'm seeing, it's kind of obnoxious. If anyone's watching this, let me know if it sucks, but I don't know. I think it's chill. Maybe I can like change my screen capture. Nah, this is how it works. So anyway, data centers, what else do we got? So like, we've got computers. So a bunch of words. There's this kind of like notion of networking. And then what are some other stuff? I know there's sockets. That's another concept I hear about when people talk about the internet. And then I'm trying to think. Those are like the main things. Like if I think about the internet, it's fundamentally that we're sending data some way. How do we do that? Data sends, what would we do? Yeah, packets. Yeah. So we're basically breaking up data. We're sending it to another computer, a network. And then it goes through an internet service provider. So there's all this like kind of, I don't know, up here, a bunch of like, I don't know, ISP and like routers. And then like, I think an internet service provider is the data provider, right? Yeah, local internet provider. How are packets sent to the internet? I know we're using packets. So I think for the sake of implementing the internet, the most fundamental thing is going to be understanding this, I think it's going to be like TCP and IP, right? Like, because basically on a computer, these are the two main things. So I think a protocol is like, it's just a bunch of rules, right? Let me just look it up. Yeah, it's just a bunch of rules about how something works. Oh, this is funny actually. He's using TCP as an example. So this is the OG protocol. Cool. So like, so I imagine like TCP is the rules about like how data is sent through the internet, and then like IP I know is internet protocol, which is probably relevant to the internet, and I think it has to do with like addressing, right? Because you've all probably heard of like IP addresses. So protocol. Let me see here. Internet protocol. I already donated, guys. Chill. Okay. So zoom out a sec. The reason I think I haven't delved deep enough into how the internet works is because you're just met with this, like just basically a shitload of acronyms. Like you just get smacked in the face. You're like, how does the internet work? And then it's just, here's the alphabet. And I'm like, no, that's not what I wanted. Like, come on. Like, why is this so complicated? Why does everything have to look like it was created by the military? Actually. Yeah, who designed the TCP IP protocol? So it's these guys. Oh, it was designed by DARPA scientists. So it is the military, yeah. I was thinking when I said that, I was like, well, why does this look all so militaristic? And it's like, well, it is. Okay. Yeah, it says it here too. Okay. Well, isn't that quaint? Okay, so basically we gotta eliminate a lot of the nonsense here and focus on like what actually matters. I think there's this fundamental thing I'm still not getting, which is like data is sent through the sky or somewhere. It's sent through a wire. can kind of like write out like sky, wires, I don't know. It could be sent through water, it could be sent through anything. It's just data being sent somewhere. And the data is in some sort of format, right? And then the computer gets it, and the computer has to do something with that data. And so I think the first thing here is TCP versus IP. Okay, I think that's pretty concise. Oh, geez, okay, yeah. I'm trying to avoid like, that's the other word too, HTTP. This is like obviously SMTP, this is email, right? So like, I know that's the thing. I don't want to go to Quora, it's usually garbage. Oh, Jesus, Wikipedia, chill. Okay. Transmission control protocol accepts data, puts it into chunks, adds a header, and then it's put into this internet protocol datagram. Okay, so IP seems like the format of the packets and then like where they go. And then I think TCP is kind of I hear it described as like the handshaking protocol, right? Yeah, so IP handles actual delivery of the data, TCP keeps track of segments. This is a good example. Okay, so you send HTML. So TCP splits the file into chunks and then forwards them to the internet layer in the network stack. Okay, this is a thing we're gonna have to know about because this is part of networking theory, and you'll hear this a lot. There's like application. Okay, so I'm aware of these terms like application, transport, networking, data link, physical. Cool. They really like this term, so it's probably relevant in how they design stuff. Header. The TCP software in the transport layer reassigns segments. Okay. So still kind of a cloud of just stuff. Yeah. Big words. Okay, so we got this thing called like, okay. Okay, this is interesting. So HTTP is above TCP in the abstraction layer. So basically a networking protocol is just like a hierarchy of abstractions. It helps you think about what's going on. So I imagine if we like, there's probably like up here the application layer, right? And then beneath it, how do I copy? Can I delete? Cool. So it's usually described as like, I don't know, there's something like a transport layer. Let's see. Cool, there it is. In its glory. All right, this is nifty. So if we abstract this away, there's basically application layers. This is like where you write code, like your Python. You'd be doing stuff like sending, like making a flask app, for example, would be HTTP. And then once you take in packets into your flask app, right, in Python, or maybe if you're using Golang, it'd be like a Fiber app or whatever. Basically, you have a server. There's these kind of, it's all on one machine, but it's describing these levels of abstraction. So like in anything you do with computers, right, there's abstraction levels. So if you're writing something in Python, under the hood, it's being interpreted. It might end up going down to low level like C bindings or whatever. And then those C bindings, like shit gets compiled down to like assembly, and then assembly runs down to machine code. And then in the end, I think the fundamental thing is that everything's just bits, zeros and ones on a computer, assuming a traditional von Neumann architecture, not a quantum computer. Not doing that shit. Although in theory, if you understand that everything's just zeros and ones, you could implement networking protocols in a quantum computer, I'm sure. You just have to rewrite the low-level interfaces. So I think kind of the chaos here is understanding what matters in each of these. So how about we like prune down here? So hypertext, application layer protocol. So I think we need to understand like kind of a couple of these terms from each layer to know like what is going on. And then I guess the other question is like, well, when you describe the internet, are we talking about these high-level abstractions? Are we talking about the actual like physical device sending data to another machine? I think, so I'm trying to think of like objective of like what I'm trying to do here. I think the objective of, to say I've implemented the internet would be, I can send data to another computer over Wi-Fi, in my opinion. Like I think, like it's 2022 at the time of this. I wouldn't consider using wires and shit to be internet. Like it just doesn't feel good to me. So I maybe need to understand a bit like what Wi-Fi is. How does Wi-Fi work? Cool, nice. It is Wi-Fi, internet. Everyone calls it internet. Internet connection is shared between multiple devices. Okay, so what does Wi-Fi stand for? Wireless fidelity. Ooh. Space ops. Okay. Oh, there's this IEEE standard. There's this thing. I bet you this is going to tie right back into the networking thing we just looked at. Aha! Look at that. Boom. So now some of the pieces are coming together. So the physical layer, which is like how data is sent, is I think the physical, yeah, that's what physical layer means. So so okay, this is fun because like I haven't done like electrical engineering, so we gotta understand that like this I think means, yeah. So like literally, how do you send bits physically? How to send the bits. So Wi-Fi. What's another example of a physical layer, right? I imagine we're gonna have Ethernet here, right? So I don't know what it's called in IEEE format, but if I go Ethernet, I bet this is LAN, okay, blah, 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 blah. Standardized is IEEE, There we go. So we got IEEE 802. Is this the same one I was just looking at? Nope, it's not. 802.3. So, okay, so there's basically, okay, let's ignore these like abstruse notations, like whatever this shit means. But let's look at the fact that we've got Wi-Fi. That's that's a physical layer for communication. We've got Ethernet, I think. And again, if you're a networking junkie and I'm botching these terms, I apologize. I'm just trying to like, I think what matters here is like simplifying stuff and not being scared by it. Data goes through the sky. So it's just like simplest reduction goes through wires. I think that's my understanding of like how Ethernet works. Let's just make sure that's not completely wrong. Yeah, okay, Wi-Fi is wireless. Ethernet over a cable. So I don't care about, oh, hey there, Andrea, welcome. Yeah, we're implementing some internet from scratch. So yeah, basically I have no clue how to do this. So we're just like, we're diving in from first principles. We're gonna take the project wherever it goes. There's no real destination. It's just the joy of trying new things. And this is something I've been wanting to learn about for a long time. And I actually never did networking courses in my undergrad, so it's kind of been like a low-key guilt. Where we're at right now is like just understanding what the internet is. We know it's like sending data to another computer. We know that it gets really complicated with all these like networking terminologies, and just like look at this, like the amount of history you need to understand. But we know fundamentally there's like using wires and not using wires. In terms of scope for like what I want to do, I obviously can't build everything from scratch, but I know I want it to be wireless. So let's just like kind of highlight some requirements of like what it means to implement the internet. So we're gonna do wireless because that's cool. We're gonna send meaningful data, like a cat pic or a text. So we're gonna send data that contains a description of a cat or a picture of a cat, because I don't know if images are really hard to encode. And then we've also, okay, so there's this other distinction of like, yeah, basically for context right now, I'm just trying to figure out like what I'm doing here. At the same time, understand what any of this is. I'm really just preventing myself from caring about these like standards, because I already know, like I've worked with the military. These people just create a bajillion like acronyms to just like in numbers and decimals to describe everything they do, because it sounds fancy, I guess, or it like works on proposals. But like as a developer, I just don't want to think about that. I think it just honestly scares people away from looking at networking, because you think, oh, I don't understand these words, I'm not smart enough. And it's like, nah, it's not that complicated. Like, let's drill into Wi-Fi. How does Wi-Fi data work? It's radio signal. Let me confirm that. Does Wi-Fi use radio? Okay, so Wi-Fi uses radio signals. That's nifty. So let's refine our model here of how this internet works. So originally I described it as data's being sent through the sky, water, or wires. I bet you data actually could be sent through the water. I don't think anyone's done it, but like if you look at it from first principles, can internet packets be sent through water? Like I don't see why not, right? So okay, I'm just curious, like, okay, this is kind of a tangent, but there's no there's no project scope, so there's no such thing as a tangent. Which is microwave ovens use. Water will absorb waves, so it will work underwater. It's not very far. Okay, wait a sec. So is Wi-Fi using radio waves or microwaves, or are these the same thing? Now we're getting into wave theory, which I actually don't understand. Radio waves. Okay. So we drill into this. Radio waves. Radio waves versus microwaves. I need to understand if these are the same thing. Okay, so no, they're different lengths. I bet Wi-Fi could be sent using different waves. Okay, the thing here is like I just don't understand signal theory. That's a thing. Do radio waves work? Let's just drill in a little bit to kind of like have some understanding of what a radio wave is. Like again, like I'm talking like minimum 50% knowledge. I know there's amplitude, I know there's physics, I know there's like, let's see. Ooh, 1920s, it's OG. Electromagnetics, yeah, so that's physics, cool. Now we've hit physics. And a radio signal is an electronic current moving back and forth very quickly. A receiver picks up the field and translates it to sounds heard through the radio. Nice. So that's how you like translate the Russians or whatever, if you're in like the war. Or who were translating who at the time? I think it was like England. I think it was England and Russia, or like there's like code breaking and stuff. Okay, we don't need to go down into radiation. I don't think we need to understand that to build the internet, but physics is a thing. The better we understand physics, the better we're gonna be able to build the internet. But yeah, it's important not to go too deep. Like we don't need to get down into like mathematics or something, right? Longest wavelengths. Oh, cool. Radio waves are the longest wavelengths in the electromagnetic spectrum. Is that really? Why would that be the case? Can't you just have infinitely long? Well, I suppose it is defined as very low frequency waves, right? And I think the frequency is how often the waves like smack, right? Like if you look at the ocean and you're like, how quick does a wave come in? That's like the same concept, right? So gamma waves would be like these like tiny little things, give you cancer, make your hair fall out, bad stuff. Probably make your body temperature go up, right? Because they're hot, I think, because they're fast. And then radio waves are good for sending data. And like, I know that you go down into like, there's like, what are they called? Fourier transforms, and like, it gets really funky. You can like combine waves without them interfering, and it's like super cool. And then you can like denoise the waves to figure out where data is coming from. I don't think this matters for the scope of implementing the internet. We can kind of assume that like people in the 20s have solved the internet. So I think maybe one thing here, if we scope out, assume we have technology available as of 1980s, but nothing more. I think this is a fun constraint. So like if it was 1980, when was the internet made? 83. Okay, so let's move this constraint. How about 1990? I want to have some abstractions. So like I want to be able to build the internet using C++, and I believe C++ is, or I think technically 83. Ooh, wait a sec. Wait, hold up. So also McGill University. Damn. Flex. Bell Labs. Oh no, it's Bell Labs, not McGill. I was like, did McGill University make C++? The hell? The hell? What month did C++ get made? Okay, it was not standardized in 1990. It was absolute garbage. 1980s. It was in 1983, right? Okay, so basically I was just like, this is kind of cool because it looks like it came out, first appeared in 1985. Okay, so there's like different working definitions. It was around the same time as the internet. That's kind of cool. So like C++ is the language of the internet. If you look at other languages, like when did Python start? Was it 80s as well? 89, a bit later. Okay, so technically speaking, if we want to build this, we can use C++, we can use Python. I know Golang's really nice for networking. It's 2009. Nope. Too new. Golang is a nope. No gophers in this video. But Golang's a great language. Just to be clear, if you're doing application programming in production, highly recommend Golang. It's better for concurrency handling. It's basically like if you've done concurrent programming, Golang has all the primitives built in for stuff like queuing, mutices, semaphores, versus if you're doing something like in C, I think there's still like, there's primitives, they're just like much more flaky. It's easier to shoot yourself in the foot, essentially. With Golang, it just handles stuff. You can write like a fan out logic in like 20 lines of code that distributes across 100 threads, and that's because Golang under the hood, how it schedules threads is different than like something like Python. We don't care about performance for the internet, so performance doesn't matter. Performance doesn't matter. Okay, so let's define what performance means, right? It's a buzzword. Latency matters, or latency doesn't matter. Reliability matters. So I want to make sure data gets to the other machine. I don't really need to. I don't need to like have it be performant, because I imagine there's probably like people that have spent the last 20 years of their life making the internet faster. I also don't care about So basically, reliability matters. Does data get from X, A to B? So latency, throughput, don't matter. So the other constraints don't. I'm limiting that because it can get really complicated to be like, for example, the problem of sending a large file is probably very different than sending a packet, right? So I think our fundamental thing would be, and I mean, I already said I want to send a cat pic or text, and text is probably going to take multiple packets. So we could look at like, how big is a networking packet? I imagine it's probably either standard or it's different for Wi-Fi. Wireless network. Actually, like, what are packets? No, actually, the better question is what protocol defines packets? Like, where does this come from? Okay, cool. So IP, this makes sense. For routing and addressing packets. Okay, I want to keep that noted. So like, rules for routing plus addressing packets. So it's where they go, how they go there. So that's what IP does. IP says when you have data, where does the data go? How does the data go there? That's IP. Now I think we can probably get into like TCP. We don't need to know all these subversions, blah, blah, blah. Oh, this is a nice diagram. So yeah, application, you have a cat picture. I think TCP seems like it's breaking the packets. It's breaking stuff down into packets. That's the proper term. Here, they're going to describe it. It dictates the way data is sent and received. Okay. TCP, the way data is sent and received. So how does that differ from routing? Well, routing sounds like the kind of like if you're sending mail, like you would tell the mail service, say it was like Amazon or the United Post or whatever they're called, wherever you are. They have their own way of getting the mail to the recipient. They need to know where they are, and they need to know how to drive there, like down the roads or whatever, or fly. And I guess you could imagine like the roads are like Ethernet, and the flying mail somewhere is like Wi-Fi. It's like the sky versus wires. And then TCP and IP sounds like the post office. So it's like, what mail needs to be sent? How do we actually package up mail? This is actually sounding a lot like the post office system, which doesn't surprise me because it's a bunch of like military people that were sitting in post offices sending letters during war and stuff, coming up with these standards. So the fact that it's so similar it's likely not a coincidence. Yeah. Other transport protocols can be used. So I imagine there's other things on top of TCP. I just don't care. Like, okay, so like, yeah, I know there's UDP. UDP is something, if I recall correctly, UDP is like, it's a different type of handshake. So handshaking is a fundamental part of how TCP works. What is the TCP protocol? Let's drill into it a bit. See, Wikipedia is always daunting. I want to find like a nice, Khan Academy is usually an amazing source. Fun fact, this is like, Khan Academy is the only place I learned mathematics. I failed all of my school in like junior high. And then in high school, I didn't go to class. I purely used Khan Academy. And then life got a lot better. It's pretty cool. Highly recommend. On top of IP to ensure reliable, yeah, got it. There's that reliability word. We need this. Lost packets, out of order packets, got it. This makes sense. Prevent lost data. Order packets. Let's not say data. Usually I try not to be a stickler on terms, but in networking it's so rigid that like it's kind of important to get right. Also, cool. We have folks in here, so. when data is sent using TCP, this is a nice diagram. So IP data. Okay, so there's these different abstraction layers. TCP has a bunch of, it's basically a struct, if you're familiar with C. It's got some fields, right? So I'm kind of thinking about implementation a little, right? Because I'm in the back of my head thinking, how do I code this, right? And now we're getting into the parts where I'm familiar, which is like, how do you work with data and stuff and code? So this is a struct. It has some fields. These fields matter for different reasons. We don't need to know exactly why. And then this IP packet gets broken down into like, is this the same thing? No, so IP data contains the TCP segment along with the content. So the cat picture would be here in data. And then there's a bunch of metadata about the cat picture. But this actually still doesn't make sense to me, because how big can a TCP segment be? Cool, this is exactly what I want. Three-way handshake, I mean, that sounds relevant. Yep, that's a thing. Let's skip these terms, we don't need to know syn and ac, whatever. Okay, basically they send data, they sound like they're agreeing that they want to receive or send data, and then they do it, or packets, pardon. Cool, they're sending headers, then they're sending the packets. So they've done a handshake somehow. They've agreed they're sending packets, and then a packet is sent over TCP, so that's how you describe it. Then the other machine acknowledges that they received it. Again, that makes total sense. Close the connection, cool. Can detect lost packets using a timeout. Okay, so actually let's scope this down a bit more. Again, we're trying to like narrow out, I don't want to be doing 3 months of work. I'm trying to do this in like minimum hours as possible. So reliability matters at least once. Okay. So what I care about is data gets from A to B at least once. I'm dropping my constraint of needing reliability just because I can already see how much of a rabbit hole this is. And I'm saying like MVP, right? So I think, yeah, the kind of meta thing we're talking about here is scoping projects, right? So building the internet is a big thing, right? We don't want to ship this in a year. We want to ship this in a day. And usually, even if you target a day, you scope it as well as possible, it's still going to blow up and take like a week. That's just how things tend to be. So trying to remove as much scope as possible. Out of order packets. Yeah, out of order packets seem complicated too. So, okay, do we need out of order packets and lost packets? We do care about lost packets. So I'm going to define it as payload. It gets from A to B at least once. So let's maybe, instead of saying what we're not doing, let's say what we are doing, which is payload is broken down into packets. All the packets get to other machine. Message is recreated. I think that's the fundamental. So latency doesn't matter. Lost packets sometimes is fine as long as it works at least once. What else? And then ordering. I feel like ordering is going to be in scope. It's going to be a thing that matters. Yeah, I mean, but basically there's handshakes. There's like a bunch of stuff happening here. And I think the one thing I'm still really curious about is like the physical layer. So like, Let me see. I think it's probably something in between transport, because transport's TCP. Okay, yeah, so what I'm not understanding, which makes sense, there's two layers I haven't looked at, is networking and data link. So networking is IP. Okay, so we have data, gets broken down into packets, that's IP. And then here, now it needs to be somehow like put into, I don't know, like a register or something so that it can be sent across Wi-Fi. Because what's gonna happen, right, if we draw this out, is these computers actually have like Wi-Fi drivers on them. How do I? Yeah, this is gonna be the what is it called? The data link layer, I imagine. Wi-Fi drivers. Let's see. Yeah. Yeah, it seems like it. Okay, cool. So devices, again, the physical device runs, this is that, I recognize that this is Wi-Fi, right? If I look it up. Yep, cool. I'm starting to recognize the numbers. So you have a driver. Again, if you're not familiar with like, what is a driver? You can define it. Yeah, a drivers basically glue together the operating system and the hardware. So it's the lowest level thing. It's the lowest level like kind of app that you would be, not app, it's an overloaded term. It's the lowest level piece of software you'd be writing to work with hardware. So typically they're really boring. They're like, the hardware has like a physical register or like a memory that you need to set like on its circuit, and the driver just like sets that bit. So maybe it'll set a ready bit to indicate that the device is ready to receive data. Maybe the driver will be like making sure we don't send too much to the hardware. So for example, if you're trying to do like matrix multiplication and you have a CPU and a GPU, you'll have different drivers for CPU and different drivers for GPU, because you have to like change how you're doing multiplication on these different hardware. Anyway, that's the point, but that ties in pretty nicely. We're going to be down in this level, I imagine, at the start. So we're going to be writing a Wi-Fi driver, basically. So I think, well, let me see if it's in here. Those are requirements. Wi-Fi driver. So what are these are the different components we have to build. A Wi-Fi driver, we have to implement TCP, right? Because like using TCP doesn't count. That's not how this works. So let's see if the stream's still going. Cool. We gotta implement TCP IP protocol. We've got, I think another part of this is like, so nobody thinks about stuff in terms of TCP. Everyone thinks in terms of HTTP. So you need to understand what this is. Hypertext Transfer Protocol, very popular, right? It's in the web URL. This is super high level for context. We're up here, right? HTTP. This is like application layer. This is like, I don't know, your Flask app, right? I don't know what presentation layer is. I really don't think this matters. Oh, but ASCII. Yeah, we all know what ASCII is. That's just characters. Let's look at it. I lied. It's like, it doesn't matter, but I care. I want to know what it is because it's here. I think session layer is almost just like a placeholder. It doesn't look like it has. Oh, never mind. It has things. People care about this. Request and response with yeah. So, okay, for context, let's try and think of how to explain this in the simplest term. Again, without the networking terms. Computer sends data to another computer. Computer receives data. Data is sent between processes on computer. So this is basically the session layer, I think. Right. So this is like, actually, let me sanity check here. Let's close some tabs. Yeah. Okay, so we have this thing called application layer and session layer, basically the easy layer. So we're sending stuff between processes, right? So this might be your web server is sending data to a queue, or like there's stuff going on, there's networking happening on your individual computer. I got like a beep, that was interesting. And then there's gonna be the connection. So there's TCP, which I think it's called, what is it called again? we've got such a rabbit hole. Transport layer. Okay, so this is the one where I think the crux of the internet is gonna be, right? The layer of control. Yeah. Yeah, look at how complicated they make this. Oh, actually, I wonder if this still works. If you're not aware about this, they might still have it. Simple.wikipedia. They don't have an article for it yet. Okay, so like for context on Wikipedia, you can go somewhere, and it's like they have this equivalent of Wikipedia called simple.wikipedia, and it just simplifies everything. It's amazing. So like if you look up cats, it's like, this is still complicated, but then if you go to the normal Wikipedia, it's like, yikes. Like it makes you feel like you don't understand what cats are. And I know what cats are. I feel like, at least I have a conceptual meme understanding of what a cat is. So I have a functional cat corpus of knowledge in my head. Yeah, I like this Cloudflare description way better. So TCP, like this is the real, I see why this is called the internet, like TCP and IP, because you could split this as like, so computer receives data. So this is like, and then it has an application session layer. So it's moved around on the computer, and then it's TCP, data broken down into packets. And we figure out how to share that with another computer. And then we've got, let's go back to this. I feel like we're gonna have this open for quite a while. Yeah, transport layer. So that's a big thing. It's not TCP. TCP is a subset of the transport layer. We're implementing TCP in this example to like scope it. And then we've got basically these like 3 low-level abstractions, which are break stuff down into packets, figure out how to handshake it, send it to another network. I think for the sake of there's so much here, right? Like if we had to break this down. So we get to basically think about like which thing are we going to implement. I personally think, okay, so constraints. Physical layer. I don't have soldering irons. I don't have like hardware with me to like I can't build like a Wi-Fi router or like a device, like a physical device right now. So let's assume that the physical device is given to us. Let's assume we're given a Wi-Fi hardware, Canon mock. So you can do this thing where you can like mock physical devices, right? Like that's what a virtual machine does. Is it like, it basically, you don't have the hardware on your computer, but it virtualizes the hardware. So it gives you the same interface. That's why interfaces are important, right? Because you're establishing a contract between different parts of your computer. And if they break that contract, it would be like imagine you go to a restaurant and you ask for a drink and they bring you the bill. Like that violates the contract, even though it's implicit. The contract is that you order your food first and then you get billed. You don't like get billed and then decide what you want. So same thing in a computer. You have to have all these like agreements basically. And if you have clear agreements, then you can actually build fake versions of hardware that agree with all the things the software wants, but it's not really doing it. Like it's not sending the packets. And so, for example, I mean, a deep part of me wants to actually send data over Wi-Fi. Like I don't feel like I'd be content if I wasn't sending packets over Wi-Fi. I don't know. It's just because like we're building the internet. If you don't send packets over to another computer, what are you doing with your life, right? Like it's not the internet. So I feel like that's a minimum need. But I'm trying to think of like the first thing we build might not be that, right? Because, or it could be actually, could think of like, if I had to think of like what defines internet from the corest thing, it is sending a packet to another machine. So in my opinion, we should be at that level, that low level. The rest of these things are just nice abstraction layers. So you got to keep in mind, like this physical layer is all that matters. Like putting something on a hardware, sending it to other hardware. That's it. Radio waves. So we need to understand waves. Everything else is an abstraction, and we can pick what parts matter for the sake of like building, like what's fun, what can we actually hack on right now? Because I imagine like hardware is going to be very slow feedback loop, but like this is the core. Like if we're trying to build the internet, we need, I guess we'd also argue we need like a networking, maybe something like data link. But basically the higher level you go, the less important it is. The higher level abstractions are tools. They make life easier, but they're not the thing you actually need. So, but at the same time, if all you do is operate in the physical layer, you're like pedantic, or like if you're just like rigid about never using abstractions, you won't get much done in life. So so there's a bunch of components here. I think I'm gonna try and just do the whole stack because that makes it feel cool. Because I also think from a pedagogical standpoint, to understand how the internet works from a modern web dev lens or a modern like developer lens, we need to understand all these layers in the most fundamental part. So like we should probably be saying, let's pick one of these, which I don't even know what these others are. So let's use HTTP. Let's use yeah. So yeah, that's how it was. Okay, so we're gonna receive HTTP data. This is cool. Look at this. Like, look how many. Actually, there's more. Oh Lord. Oh God. Oh, this is ridiculous. Look at that. Look how many protocols there are. Look at this. Oh my God. Can you believe? Holy crap. Wait, let's go down a rabbit hole time. Look how many protocols there are. What is this? What? What? Okay, so this is HTTP. Like I get that. Everyone knows HTTP, right? There it is. Cool. But like what is okay, Telnet. I've heard of Telnet. Application protocol for internet, local area networks. Okay, but then what is like this? What is going on? Look how many there are. Oh, like, wait, there's even like instant messaging. So, okay, are there any we recognize here? So there's Google, Messenger. What? Can I like, does Messenger have its own protocol? No, this is like, there's no way. What? No way. Come on. What? Okay, this is, I don't know if anyone else is like, there's not many people here, but like, I don't know if others find this as cool as I do, but like, yeah, like they're not using HTTP. What? When you realize that, like, okay, look at this. Like, we're only taught this one thing. We're like living in the matrix. There's so many. There's VoIP. Yeah, I recognize that. Uh, there's so many protocols. Okay, I'm just gonna go down this for a little bit. This person's from Facebook. Cool, I'll trust you. Uh, Quora person. Okay, so chat windows are done in HTTP. No, I'm curious about the MQTT protocol. We're not going to build this, but like, okay, but like, come on, how cool is this? Why do they have this, right? I bet you that there's like latency or like storage constraints that IoT devices have, and so they're like, you know what? HTTP doesn't work. I'll see. Thanks for swinging by. Yeah, I think this is fascinating. So like, um, yeah, I'll definitely, yeah, for context, I'll definitely post a video after and maybe blog like a summary. We'll have to see where this goes. I have no clue where this is heading. Um, but depending on the destination we reach, I will do stuff. Okay, but I'm gonna go down this. This is cool as heck. Okay, so I get like a specification is just a bunch of rules, boring stuff. We can read it a bit just to see what these rules look like. I don't know anyone who reads these for fun though. Like I don't even know anyone who reads these, right? This is cool though. So like uh, MQTT, so it just becomes packets, right? Like everything is a packet. Um, does it use TCP? Cool. Check this out. Okay, so MQTT, it's a higher level abstraction. It breaks down to TCP and IP. That's the thing y'all know and love in this stream. That's the, where is it? Oh God, it's becoming, oh God. That's the transport layer. I already remember it, yeah. Transport layer. So we have this completely different protocol, different packet format, and it breaks down into the same packet format, which is pretty cool to me. Um, you can see how long this proposal is. So what I'm trying to get out of this is like, how does this differ from like how do application protocols differ? Um, so they're defining packets, and then I guess TCP is breaking down packets. So these must be adherent to the TCP interface. Uh, they're saying here's the data, here's how we break it down into smaller pieces of data, and then TCP is going to say, okay, cool. How do we send this as how do we make this match the IP protocol? And then handshake to send these packets. Like so, once I have data, again for context here, I think we can say packet. I think it's a safe. I imagine there's a standard interface here, right? Yeah, see, we saw this earlier, right? Um, we saw this exact diagram like an hour ago, back in like when we were just exploring, yeah, like around here. Um, so TCP packets look like this. They have some data, they have some cool stuff. We should probably start collecting this because, okay, so I think something neat that's gonna happen, which, oh, welcome, Manuel. So something funky that's gonna happen is you're gonna realize that everything in computers is just packets, or everything's just data. Everything's just zeros and ones in a computer. And what we're gonna figure out is that networking is just like this whole abstraction layer here, application to physical. It's just changing bits, zeros and ones, into different shapes. And it's using letters, right? But you gotta remember that letters are part of ASCII, and ASCII is just a bunch of zeros and ones. Every letter, every single thing on the keyboard is just a zero and a one, some combination. And all this networking stuff is doing is it's taking a bunch of zeros and ones, storing them in a block, and then it's like changing them around into different ways, and then sending it over a physical device through the air as radio waves. So like if we go back to our understanding here, let me redefine it. So we go back to what is the internet? So we're describing transport layers and stuff. We could just say computer breaks data into packets, sends packets around into lower level forms, right? So it does here, transport, and now we were saying packets before, but we were realizing that TCP has its own packet format, IP has its own packet format. So my understanding is a packet, what is a packet? I think it's just it's a formatted unit of data. So this thing that we're calling a packet isn't one thing. It's actually just a data structure. It's a struct of bits, and each region of the bits mean a certain thing. Okay, I feel like this is a concept where anyone watching this later might be like just mind blown. Like this is like one of the fundamental mind blowing moments of computer science that I feel like if anyone's taking like computer science, this is like something you'll learn, is that like everything's zeros and ones. I think it's worth drilling into a bit. So like to explain it in the simplest terms again, because I think I basically glossed over it. I was like, yeah, everything's zeros and ones. And then people are just like, okay, cool, but like, what does that mean? And like, this took quite a lot of explanation to get in university for people. Okay, so literally, okay, I'm gonna make my own packet format. So we're gonna do a tangent. I'm gonna make a tangent section. There's gonna be tangents in this. Okay, so you can have a bunch of zeros and ones. How many do we have? Let's make it consistent. So 1, 2, 3, 4, 5, 6, 7, 8. So we have eight bits, right? You could say that this represents the letter A. So we're gonna say, we're gonna create the Morse code. Not Morse code, like based on my name. Yeah, I know, clever, right? And we're gonna encode letters, right? And we can do this in like the most simple way. You could just say this is A, you could say this is B. Also the reason it's zeros and ones is because there's no, like you can't have a 2 in binary. Like it's a base 2 number system. That's the premise of what it means to be base 2. I don't have enough time to explain base number systems. That's probably like 2 levels of abstraction down of like, you just got to go grok that because it's kind of a little hard to wrap your head around. Basically, there's strings of numbers though. They're either zeros or ones and each represent something. We could say it's 16-bit. We could go like, we could say that. This is a pretty thick data format, right? So that's why like 32 versus 64-bit matters, because under the hood, everything's a 32-bit string or 64-bit string. And if you only need like, say you're just storing the alphabet, right? You don't even need 16 or 8 bits, because 8 bits is 2 to the 8, right? Which is like, I think it's like 1,000 something, 1,040. I can't remember the exact amount. 2, 4, 6, 8, 16, 32, 64. Okay, well, it's not that much. It's like 256 or something. Which actually might make sense is, yeah, ASCII's 8-bit. Boom, y'all heard it here first, folks. But then Unicode, okay, so basically ASCII is just all your data is letters and it's stored using 8 bits. So there's, okay, I'm gonna do the math now. 2, 4, 6, no, 2, 4, 8, 16, 32, 64, 128, 256, 256 combinations, 8-bit. That's my understanding. If that's wrong, I am dumb. I'm not a math major. I was a math minor, so I don't know how to count. But you can have 256. Now you might be thinking, well, Unicode, like you gotta send an emoji, right? You wanna do like smiley face? Oh, Jesus Christ. This is terrifying. I'm not using Google anymore. This is awful. Holy crap. There we go. You can paste this in your web browser, right? Nice. And then, you got all these emojis. We love emojis. Well, I'm not accepting cookies. Okay, so basically there's hundreds of emojis, right? And so that can't fit in ASCII. So you might be thinking, well, then what do we do? And it's like, well, the answer is we use Unicode. And Unicode has a bunch of different combinations. So each of these, again, there's basically like a number. So imagine it's like 0, 0, 0, 0, 0, 0, bunch of zeros, 1 is equal to this. And then different browsers render it in different ways. I'm kind of going down a tangent, but just like, whole premise is like this same thing, which represents the number 5, is corresponding to this emotion, and then every different computer can represent it however it wants. It's kind of cool. Like we're giving computers emotions, basically. I don't know. I think that's pretty bonkers. Like imagine when like neural networks read these and start understanding emotional sentiment in computers, and they start developing their own encodings of like how machines feel based on emojis. I think it's cool. But anyway, if you look up the number of bits in Unicode, guarantee it's not 8. See, 16. So you can have an 8-bit. I'm certain 8-bit doesn't encode all the emojis we want, right? Because we already know this. 16-bit, on the other hand, if I go open this up, can I do this? We're opening code finally. 2 to the 16, 65,000 combinations. That's pretty reasonable, right? Then you imagine a 32-bit machine. Okay, like that's a lot of emojis. You can pretty much, I think, express any color on the color spectrum using that. So like that's the whole premise, is like emojis need a larger number of bits because there's so many types. And then if we really tie it back into the core thing we're trying to do. Oh, hey, Eric, welcome. We went on a tangent. We were talking about, okay, so we went down like 5 tangents on the stack trace. So let's backtrack. I was talking about how bits are encoded because everything's just bits. And I think this is like one of the things I'm spending time on because people don't realize it. Like they don't really realize it. Once you realize everything in a computer is just zeros and ones and it's encoded in different ways, then you realize all the internet is a computer receives a bunch of data, zeros and ones. It breaks the data, or it encode data into some format, right? You could be like smile. You could encode it in any way you want. Catpic.png. You can code the data however you want. It's all zeros and ones. And then networking, which is this complicated thing. Where was this? The OSI model. Again, apologies, I've Googled this like 10 times now. This OSI model. So again, all this confusion, HTTP, sockets, TCP, IP, holy shit, so many things. Got to understand it all. It's all just zeros and ones represented in a different way. So watch. We were already showing, let's close some of these. We were showing Facebook has their own format they're using. I don't know if it's actually theirs. They're using this format though, MQTT. And then if you go into here, the big realization was that they have their own packet format. And then if you search for TCP, where is it? Yeah, so we support this. Okay, so basically, this is just a high-level format. It's defining what packets look like. Again, zeros and ones. Here's the bits. A byte is just 8 bits. And this gets converted into a TCP packet. Change data into TCP packet. So every computer does this. It takes, at least if it's using TCP. Again, we're focusing on that. It's taking a bunch of data, cat picture, emojis, whatever, music. Let's put like sandstorm.wav. So it can be music, anything. It's just zeros and ones. Like if there's one thing you remember, it's that data is just zeros and ones. And the same zeros and ones could mean 100 different things. So we take those zeros and ones, we organize it into a packet. We look up the TCP packet. What does that look like? Well, I bet you it's going to describe it here. There it is. Bada bing. This is actually so awesome that we're going to screenshot it. Oh, wallpaper. So again, like don't get bogged down by all this noise. There's like, what is a checksum? Oh, what's a data offset? Oh, I don't understand. It's like, no, chill. Like, it's just zeros and ones. The little parts of it, like the first 8 bits mean something. Well, actually, you can see here they're describing it: source, port, destination, port. So ports are a thing. Don't fully understand what they are. They're kind of like little socket. Like let's not say socket. Okay. There's a bunch of words you need to understand. We're trying to learn what matters here from scratch. So we don't need to think about every single word and get stuck. What matters here is like zeros and ones. This cat picture, this smiley face is going to get turned into, let's see if this works. How do I? Boom. So this cat picture or wave or whatever, we could even, it's going to be represented in some format. I'm actually curious if HTTP has a packet now, because based on my understanding, again, like I'm not trying to like teach this, I'm literally trying to understand this. So if I'm not making sense, it's because I also don't get it. I bet you HTTP has a packet format. That's my guess. Like because HTTP is just something, it's just some way of, like I'm still trying to understand the application layer. Yep. So it's representing packets in some way, like in some format that's like nice for us. These are obsolete. Maybe we want to use, also HTTP3 is coming out. Let's look at this. I'm trying to see if there's like a format, a packet. Like how do I send data in HTTP2 format? Oh, look at this. We're in Web 2. I hope this, sorry for all my Web 3 friends. This must be really upsetting that like we're talking about how to do Web 1 and Web 2 right now, but deal with it. Gotta understand the OGs before you get to Web 3. Cool. Okay, so HTTP2. So, okay, point I'm trying to make is I don't understand how HTTP works, but I understand now how packets work. And so from that, you can deduce what HTTP is, right? HTTP is just another way of codifying data, right? So here it is, headers, just a bunch of metadata. Like, okay, HTTP has like post requests, get requests, whatever, storage, put, like all these things. Don't need to know it all. But in the end, all it is headers and data. So in this case, the headers are all these like, where is it coming from? The data is like, hello. And then this is gonna get, let's actually screenshot this too. I think this is gonna end up being a blog post. There's a good recommendation from someone in the chat. So basically, right, let's just look at one format. We're gonna be implementing HTTP. Right, this is gonna get broken down into this, a TCP packet. And then TCP like basically sends this to another computer over Wi-Fi. TCP packets sent over IP one at a time. So packets, this gets broken down into a bunch, like whatever our data is, say a cat picture, broken down into some payload representation. The payload representation is going to get broken down into a bunch of individual packets. Each of those packets is sent one at a time over, in our case, it's going to be a Wi-Fi driver we're going to write. And then the Wi-Fi driver is going to it's going to generate radio waves that are sent to another computer, which interprets them, builds it all up in the same way back into a cat picture. So that's how it works. Like that's how the internet works. And all these terms in the middle are just like the military trying to sound smart and like have complex protocols. Because probably you get like a promotion if you design something cool during your tenure. And so like the incentive is to design cool protocols and like battle them out. And also keep in mind, like, even if, because this is, now we're getting into like almost sociology here, but like if you look at Web3, right? There's so many arguments about Web3 as the same things happening. So like Web 2, Web 1, there's all these like, buzzwords. There's like DeFi, there's like all these different there's protocols being set. Like, I bet if I look up protocol for Web3, there's probably like just a load of protocols at this point. I don't even think it's been established yet. So if you're building in here, you just understand it's the same as Web 1, Web 2. It's just like people design all these protocols. Some of them are going to suck. Some of them aren't going to suck. Some of them are going to get used. Yeah, that was Eric just walked by. I don't know how he's in the stream and just walked out of the house, but props to you, Eric. That's impressive. Parallelism. But so basically, okay, let's do like a global recap. I think people are scared of the learning how the internet works, because when you Google how does the internet work, you get this. You get like 40 acronyms. No shit, that's scary. Like, this doesn't mean anything. Then all you do is you realize that each of these acronyms just represent some fancy way to take a cat picture and encode it as zeros and ones in some way, right? So we described it. We said like, there's this way, like HTTP, it's a format. You have info about the URL, like the website it came from, the way it was sent, how long it is. And then you have a format like JSON, like I can't remember the acronym, what it stands for, JavaScript serial object notation. That might be it. Anyway, then there's a data payload. This is like your cat picture. This goes down the abstraction level. It goes down into like sockets, goes through all these different funky things, hits TCP. TCP is just like the low level way of representing everything. So everything comes down to this. If you're Facebook and you're sending cat pictures, it's got to turn into a TCP packet. If you're making a web server and you're using HTTPS, you're using a funky secure protocol, doesn't matter. You got to turn it into packets at some point. And I think there's a few of these different ways of doing this. So like TCP, UDP, SCTP. I bet you one of these is like a secure version. Stream control. Because like there needs to be a way to encode. Well, so I guess, so HTTPS, like the secure one, which I don't even see. Basically, let's not go down another rabbit hole. Let's summarize. You see, this is, welcome to ADHD. The summary is like data's just turned into other different formats until eventually the data is just this really boring format. Called like, I guess we can call it like IP, networking layer. IP is really boring, right? Let's look at like IPv6, let's pick one. There it is. Yawn. Look how tired that makes you look. Like, look how beautiful the previous formats were. You got like colors, you got complexity, and then you get down to IP, and it's just like, here's where it came from, here's where it's going. All right, source address, see in this format, source address is example.org. And then once it's broken down into a smaller packet, source address just becomes like a bunch of bits, right? Maybe it's representing an IP address, right? Like 192.168, 0. whatever, or probably for a non-local network, it's going to be some other series of numbers. Again, they all mean different things. Don't get caught up in the meaning. It's just zeros and ones. And then I think the other core part of the internet that we need to understand is this data. Let's take a picture of it actually, just because, again, just to show, I think this like really adds a lot of clarity that like, this is how it works, man. Got a new picture, right? So you see stuff you're familiar with, source port, destination port, there's more data, there's stuff, it's complicated, there's more bits, 480 bits here, whereas in here, there's like, no, 32 bits, nice and simple. And you can see the first 3 bits of the version. So there's, the version number can be a certain number between 0 and like 8, I guess, 0 and 7. And then there's like, I don't even know where the data is being sent, right? But there needs to be a data, payload. I guess there's a payload length. So like IP's describing how stuff's sent. There's going to be data packets, I imagine, with IP that are going to actually have the cat picture encoded in different ways. But yeah, basically this gets sent. I think the next thing that matters is computer sends data through the sky. Right? Let's just get rid of these terms. Again, like they're just blocking us from understanding first principles of what's going on. Cat picture. broken down through a bunch of complicated, nice like charts that explain how to represent different parts of the data. TCP breaks down packets to tiny IP packets, another type of packet, right? And then we get down physical layer. The physical layer, computer sends data. I think this is the part. Yeah, the physical layer. So we have the data link layer, which is sends packets to hardware. And then physical layer. The hardware sends data through the sky, right? There's other ways to do this. We could probably have, so like if you get down into here, you want to think first principles, how could we build a better internet? You got to go here, physical layer, right? So you got to look at like, there's Bluetooth, there's USB, there's Ethernet, there's Wi-Fi, which we know is 802.11. There's Ethernet, which is 802.3. This is wires. This is through radio. I wonder, can you send internet packets through light waves? Like, let's just look it up, see if people have done it. See some nerds talking about this. Use electrons, blah, 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 blah. Basically, everything here is coming down to physics. Like, we could have a whole stream just about physics of data transfer, which honestly would be pretty cool, because I feel like physics gets all the cool stuff, and then computer scientists get to like move it around in cool ways. Like we're just moving around bits, but then you get down to physics and it's like, damn, like I don't know how this works. Like what is going on? I'm actually dedicated to find if this is a thing. Li-Fi, there it is. Right, so again, first principles, now we're like, well, is Li-Fi a thing? Li-Fi uses light to transmit data. There you go. That's a thing. It's from 2011. Has it been built? Like visible light spectrums? I mean, technically it could be. You could use light. It might not be faster. Like I'm thinking of light as being like super clever and like. Oh, look at this. It's growing though. Li-Fi, compound annual growth. I mean, this article hasn't been updated since 2018, which is a flag that it's not working. Oh yeah, so you're gonna get different communication limits, right? Right, because like radio is gonna suck when you have obstructions, because radio waves don't like going through dense walls. Li-Fi can't penetrate walls and doors. Same thing. I mean, I bet you, can you build internet using sonar? Right? That's another type. That's sound, right? Who's this person saying you can't? Kiss my ass, bro. Just because this person says you can't. Where is it? It's just in the comment description. I don't even see it. Do they delete the comment? I would delete a comment when somebody says no. I think the answer is very rarely no to technology. I think it's more how. I'm basically just going down and looking at like how could you send packets through the internet? Because like once you realize it's just packets, we can probably do this in a lot of ways. Like, all right, what's the other? There's light. There's sound. Water isn't like a wave, I guess. Okay, so like this is where I'm gonna be really dumb, is understanding like how. Okay, wait a sec. So like is light a wave? I'm pretty sure light's a wave. Oh fuck! Now we're getting into quantum physics. God damn it! I'm not going down this rabbit hole because I don't think physicists even understand this yet. So I'm not gonna understand it in the duration of this call. Okay, I mean, I'm gonna put this as like a tangent. Later stuff. Yeah, I mean, doing particle physics would be a fun stream. Eventually, like just understanding. This is another topic where I feel like I'm just so dumb here that I don't even know how to like think about it. It's like, what is light? Wave or a particle? Okay. It can be seen as both. Let's call it a wave. Boom. I just like I just closed 50 years of physics. And I'm just like, it's a wave because I need it to be a wave for the purpose of sending cat pics. I don't care. So it's like, sound is definitely a wave. It's just sanity check that I'm not being, yeah, sound goes through the air as a wave. Radio is a wave. This is Wi-Fi. Seems like waves are the way data is sent. Like in the end of the day, everything's a wave, which is kind of weird when you think about it. So then how does Ethernet data get sent? How do Ethernet cables work? I think Ethernet cables use electromagnetic waves. Let me see. Trying to see if that's the case. Yeah, so Ethernet cables emit electromagnetic waves. This is a cool. Okay, there's a couple like really interesting observations here. So, I mean, a tangent is in physics. Let's not say everything because I actually don't know enough about physics. Most things seem to be waves. So we've got Wi-Fi, right? Wi-Fi is radio waves. We've got sonar, sound waves. We've got Li-Fi, light waves. Ethernet, cables. Nope. Magnetic waves. Boom, get wrecked. This is kind of cool to me. So like, even when you think it's cables, it's like, nah, those cables just got waves in them. It's all waves. So I think with this model in mind, I'm trying to think of an example of like data transfer with physics that isn't wave-based. Like, set of, can you send data without waves? I think is an interesting physics question now. Because like, do you know this, Eric?
Yeah, you can.
You can, yeah, what's the way? So I'm realizing this, and I'm basically like, I'm realizing that all the ways that we use internet are just waves. It's sound waves, light waves, Ethernet, which is magnetic wave.
I mean, wave isn't necessarily correct. Do you mind if I'm like hijacking your stream?
Yeah. I would love to inject your knowledge on here, so I don't.
So hardware uses, I may be wrong on this, but from my understanding working with Arduinos, hardware uses two different types of signals. One is digital and one is analog. Digital is either it's on or it's off, so it's not technically a wave. Is there a voltage applied here? So in the case of like Ethernet, one of the lines may just have a voltage applied.
Got it.
Indicates like something is on, for example.
But then underneath though, like the way voltage is done, isn't it electromagnetism? Like it's electron flow? Which would be like a wave? Like under the hood, like the...
It's technically only electron flow if the circuit is closed.
Got it. So if it's not closed, it's like the difference between not being closed and being closed.
So ultimately what they're doing to read this, it's a voltage. They're reading the voltage if it's, say, 5 volts is standard for a lot of systems like USBs.
Yeah.
If it reads, I think it's 5 volts. If on the other end it reads 5 volts, it means that the wire is on. Though reading 5 volts can be done in different ways. You could do it with a resistor. So technically there's not much current flowing. There is current flowing. You can only ever read something if current's flowing from my understanding. That's not a hard assertion, but that's, my limited assertion. So you just have massive resistance on the other end, enough to have a little bit of flow, and through that you can register the voltage or read the voltage.
Interesting. Okay, yeah, that makes sense. So there's ways of like using the existence versus non-existence of a state to read data.
It's Boolean.
Yeah.
Like digital is a Boolean representation of electrical, and then analog is the wave.
Yeah.
So analog sends a sinusoidal wave or superimposed waves. So you could have multiple waves built together and then deconstruct the meaning of that on the other side.
Is that like the Fourier transforms and all that like funky stuff to like kind of denoise waves? Because I went back through that earlier actually in the stream of just trying to understand. So like
I wouldn't personally know that exact part.
Okay, so let me know if this is like roughly true.
Yeah.
So there's a lot of many ways in which data is sent through the format of waves.
Yep.
Those waves hit physical devices that are analog in how they receive waves, right? Because they're all, like, I don't know, electrical engineers do nerdy stuff and like make them listen. And then in there's basically low-level controllers that turn that analog's wave into a digital Boolean of 0 or 1. And then like basically drivers, then it hits software land, drivers pick it up and start using the zeros and ones. So they're abstracted up into data sent over the internet. Or
in my experience, analog converts into a range from 0 to 256. So perhaps that's just the Arduino way of doing things, and there's way better, more efficient ways to decode and like get more rich information out of the wave. But ultimately, the wave is a different way to represent ones and zeros, but you can do it at the 256 level.
Got it. Do you think to be able to say we've implemented the internet, we have to build like a hardware device? Like so I've scoped out the project into like a few things. We've basically got that there's like, there's going to be a web app, easy stuff, right? We're going to implement a Wi-Fi driver, as in we're going to send data into the lowest level packets. We're going to implement TCP, IP. This is probably going to be multiple streams, right? And then the part I'm really unknown at is the hardware. So we need to, like, if I get an Arduino, could I build a Wi-Fi relay? Like, or is that just like a crazy, like, is that something that's just going to take months?
I don't know.
Hell yeah.
In my experience with Arduino doesn't play well with Wi-Fi, but probably would be the truest representation of Wi-Fi, because you can bottleneck yourself through the electrical wiring itself. Like you're in charge of the wiring, so you could use that as, everything's got to pipe through these wires as like a restriction to basically prove that you've gone down to the electrical level. Arduino would be very good for that. You could do digital and analog, whereas things like Raspberry Pi can only do digital.
Got it. I think the other thing too is I could technically encode IP packets in Morse code and then beep. And then I could have a listener across the room that listens to the beeping. And then encodes the packets. And we could implement TCP IP using Morse code, which I think is the OG way, like pre-internet. That was like internet, right?
You get two Arduinos, completely logically separate, put a speaker on one and a mic on another.
Yeah, exactly. We could like technically have, so technically speaking, that would be internet, right? Because it's using, as long as it's using the IP protocol.
Well, internet as well. I don't know if this is part of your design spec, but
I'm not sure yet. I'm trying to figure it out literally as we go.
IP discovery, like DNS. How do you, internet for me, is the assumption is you're going out and you're querying for a specific address and only sending packets to that.
Yeah, so discovery layer. I mean, so basically this stream right now is turning into just understanding like what is going on, like what is all the different stuff, and then scoping it as well as possible. So for example, I've already scoped out packet loss, and I'm just like, okay, like all we need to do is send a payload once. We don't need fault tolerance. We don't need like ordering and like all this. It's like, let's send the packets in order, nice and simple, and let's assume that they arrive. And like, if they don't, let's try again. But like, let's not worry about all this. And then I'm more concerned with like the encoding protocols, and like I think building out like it's all about 90-10, right? Like what's the coolest subset of the internet we can build without investing in any stuff. Hey, welcome, Polly. We've got somebody else joined. And also thanks for your explanation, sir. This is, so that's basically I think the scope is coming as we go. But it's kind of this feedback loop of like, okay, I could jump in and code parts of this. Like I know I could build the web client. I know I could implement a driver. The hardware part seems like, since I just don't know anything about it, that's going to be like get hardware.
I have a Raspberry Pi laying upstairs if you want to use that.
That'd be sick, actually.
Yeah, do you want me to grab it?
Yeah, I mean, it's going to take me time to set up just to like get into it, but I at least want to see like what's on it.
Yeah.
If you could bring that down, that'd be dope.
Yeah.
Thanks, man. Cool. So now we've got hardware. So technically, we could just start building a Wi-Fi device, I think it's called. Okay, and we've got a lot of noise here. This is kind of cool. So for context, for those who have just joined, when we started the stream, the context was we didn't even have Wi-Fi drivers. The context was computer, internet. That was basically all we knew. And to be clear, I'm not like pulling your leg here. Like I just haven't studied networking. So I know all the words, and it's kind of this jumbled cloud. And it's kind of neat how in like less than 2 hours we're able to break it down to something that makes quite a lot of sense. Like it's actually mind-boggling that if you sit down for 2 hours, you can take something that makes no sense, just Google a bunch, and then it makes way more sense than, like 100 times more sense than before. So let me try and remove, we still got our word cloud here. Let's try and sort this out a little bit. And I'll probably do this outside of stream too. I'll clean up docs and just like organize my thoughts a bit better. But I'm trying to think of like where the thing is that we're most unknown about. And I think the other unknown is the order of implementing. So there's scope, and then there's implementation path. So we need to know scope, specs, and then how do we build it. So basically, what are we building? How? I think the scope here is we need to figure out if we're doing discoverability. So discoverability. Okay. Actually, I think the easiest way to do this is TCP proposal. There must be like a thing online that has this. Is this it? 1974. That seems too old because the TCP was 1983, right? Thank you, sir.
We got
a micro SSD.
Raspberry Pi.
Got a Raspberry Pi.
It currently has an Ubuntu. Here's a breadboard if you ever want to do wiring stuff.
Sick.
And here's the power.
Hell yeah, my dude. Thank you.
Enjoy. You want a coffee?
I would love a coffee.
What's your preference?
I'd love a latte, actually. I'm feeling adventurous.
Deal.
Cool.
I'll be watching your stream from afar.
How are you doing that, by the way?
I am a user.
Yeah, but are you on like phone, or are you like?
Yeah.
That's cool. I was like, because I saw you walk out and then comment, and I was like, this is a fake listener. Anyway, I'm looking at this. Okay, yeah. Also, context for those listening. Yeah, my attention span goes everywhere, so bear with me. It's just kind of how it works. I'm trying to. So we've got this bucket of unknowns here, which is like, how do you take a Raspberry Pi, right? That's what this is. Yep. And how do we turn this into a Wi-Fi device? I have no clue. I've built robots, but like surprisingly easier than doing like Wi-Fi, I think, because like I've just worked on it before. That's it. That's really the answer. If you've done something before, it's easier. If you haven't done something, it's harder. We got wires, we got the stuff. And then the other thing we're trying to understand here is like, we're still trying to scope what TCP and IP are. Because I think, again, if we go up here, yeah, computer receives data, breaks it down into some packets, and then I know that once it gets down to the hardware, sending stuff is now electrical engineering. That's totally a thing we can do. So now the question is, what is our scope in the? So I maybe we could describe it as two layers. So there's the software world, and then there's hardware world. I think this tends to be, so like in my time, I've worked on like cars, and I've worked on web apps, and I think a good way to think about things is software and hardware, because ultimately software and hardware are very different abstractions with different language. So in software, we've got pretty much all the, like, actually let me move this up to requirements up here. So we're gonna hack a Raspberry Pi. Is that how you spell raspberry? I think so. I'm not here to spell. That's not my job. And so send data over Wi-Fi. I actually have a cool idea, which is instead of using Wi-Fi, we make our own, implement Morse code pattern. I think this is personally even more exciting, is to say, hey, we're gonna build our own internet protocol for sending data. So instead of we're gonna use TCP. We're not going full unhinged here. We're gonna we're gonna use TCP and IP because that's the underpinning of the internet, right? So so basically, how do we send data to other computers and how do we encode it? That's fine. But then for the actual hardware, how do we physically get waves to go through the sky or through a wire to another hardware device? I would love to build our own. I think that's kind of cool. So for example, we could use Morse code and have one Raspberry Pi here. It could be making beeping noises, and each beep is going to represent a number. And these numbers from the beeps are going to correspond to parts of a packet. So it's going to be slow as heck. It might take like 10 minutes to send a packet. But I think it's cool as heck, man. Because like then we can imagine, okay, we beep, we're like beep, 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 beep. Like let's just look up Morse code, right? I don't need to sit here beeping on camera. Okay. Raspberry Pi, okay, I think basically what I'm getting at is sound waves are, I think, the most intuitive for humans because we can hear sound. We know what that means. Like you can hear beeps and you're like, this is cool. But you can't hear light. You can't or I guess you could do flashing and stuff. So we could technically do it. The point I'm getting at is Morse code is the underlying encoding. Morse code is very intuitive. So if you're flashing something like flash, 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 right? You get that. If it's beeping, you know. The way that Wi-Fi works is it's just sending these really weird pulses at random frequencies and then like encoding them. It's just not as intuitive. So TLDR, I'm doing Morse code. I'm not justifying it anymore. Morse code's the way it's the way it's happening. You have a problem with it, my stream. But that's the thing. I think this is a pretty scoped project, honestly. Morse code, other Pi has, so it's gonna have a, what's it called? Like, I don't know, a listener, a mic, I think that's what it's called. Yeah. That listens to Morse code, encodes packets into, I guess it's IP format. So that's the hardware. That's actually pretty simple. The rest of this is primarily, let's use a standard we're familiar with. I don't want to like hack all the standards. I like going unhinged with hardware because I think it's just kind of fun. Like with physics, you can do a lot of really cool stuff. With software, let's use like what's tried and true because I think deviating from the norm just confuses devs. So we're gonna go HTTP. We're gonna make a client, listens for HTTP request. Easy, right? Then we're going to send HTTP request to another local process using sockets. Sockets, that's another type of networking. It's local. We could scope this out maybe, but I think that's a cool part of networking to understand, just like really drill home that it's all just packets and bits. Then we're gonna implement TCP. I still don't know what that means. Then we're gonna implement IP. These statements might be really dumb depending on how much work this is. Implement Wi-Fi driver. Or we're gonna implement a Morse code driver. We're gonna make our own, we're using Morse code, right? So we're using our own hacked Morse code. And so I'm gonna make my own drivers that sends IP packets. So this is like, again, green. Okay, this is what we're saying here is like green means it's like really known. Like this isn't, I'm not breaking any rules here. This is like nice, clean networking. This is exactly how it was designed by our military friends. But then this part is gonna be where I implement my own driver that turns IP packets into Morse code, which are gonna be like this hacked version of Morse code that I'm gonna design so I can send cat pictures, and then continued on hardware. Then we go down to the hardware layer. Hardware is we're gonna hack a Raspberry Pi to take in Morse code IP packets from here. We're going to implement a Morse code pattern, and then we're going to beep it to another device. So other Pi is going to have a mic that listens for. Yeah, now I've just gone fully committed to implementing my own Morse code because I just think I just can't not do it. We can delete all this. We've got noise. Other device, so listens to it, decodes to IP packets, encodes into HTTP format, prints cat text. So I think that's the ultimate. Then I think we've done the encoding part of the internet, right? Like that's all scope. So again, like point here is I'm trying to figure out like what is like actually part of the internet, like what would I consider like a real beast project, and then I think if I had this built, I would be like, yeah, I've implemented the internet from scratch and I built my own Morse code interpreter, or it's technically not interpreter, receiver. I guess I don't know the word that engineers use here, but and now we can clean some of this out. And now I think Eric in our stream brought up a good point about how do we do discoverability? How do we do like, again, there's like up here in internet land, there are internet service providers, there are routers, there's all this stuff going on. I don't think, my claim is those things need to exist, but they need to exist in the most minimum form. So like, maybe we could go down that rabbit hole a bit and understand it. Because I think, like, let's look at like internet. Let's just define it. Like, how is the internet defined? It's a global network consisting of interconnected networks using standard communication protocols. The internet is a network of information and communication facilities with standard protocols. That's what the internet is. So in my opinion, if we can connect data between two machines using well-established protocols that the rest of the internet is using, like I can take a PNG or a JPEG and I can send it to another computer, that is internet. That might be local internet, like local area network. Or we could argue that my internet sucks because it doesn't go outside of the house. But that's also like how most internet is. Like when you have Wi-Fi, if you leave the house, you're gonna lose Wi-Fi. And now you understand why. It's because you've lost connection to this router that's in your house, and that router is just connecting to a local internet service provider, and that internet service provider. So maybe okay, I lied. We're gonna understand what parts we're not building, but we're not going to ignore them. Like I think it's worth understanding what we are and what we aren't building. And also, yeah, Eric, I highly recommend do your own stream. You do amazing projects. I would love to see. I'd love to see a stream by you personally in the hardware space, especially. A follow along hardware stream would be super cool. Okay, so I can't just keep Googling how the internet works, right? Like we need internet, how do internet service providers work? Cable, DSL, dial-up, blah, 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 blah. How internet infrastructure works. That's probably better. We're doing infrastructure now. It seems like no matter what project I take on, I end up doing cloud infra. All roads lead to cloud infra, which I think makes sense because pretty much everything is just a service built on cloud infra. Yeah, a modem. Okay, so like let's just grok a little bit of this. I mean, I think we can. We've got bits. We'll keep this stuff. I have such a tendency to clean notes. We'll clean it later. Clean it later, Kyle. Chill out. Yeah, and I think I'll delete a bunch of that. Okay, okay, we've got this rough section of like scope, and then up here we kind of have a bunch of notes. And let's just make a word cloud. We got internet service providers. We got modems. We got routers. We got data centers. Data center with a C. Let's just kind of skim this and see like what makes up the internet. Did the internet begin in 1969 or not? When did the internet start? It says 1983. Okay. Okay, so the whole premise is that computers had ways of communicating with each other. The thing that made the internet was a standard protocol. It's called TCP. So I mean, that alone just defines like the whole point of building the internet is TCP with everything else is auxiliary. Auxiliary? Like it's secondary, doesn't matter. Hardware, this is great. I want to do it just because I like hardware, but we need to start like this. TCP, IP. That's what internet is. If you don't have that, you have not built the internet, based on the definition of the internet. So that's kind of cool. If folks ever ask you like, what is the internet? You can say it's TCP IP. Like it's a protocol for how to communicate bits. The internet didn't invent radio waves. The internet did not invent Morse code. It was the military in a bunch of battles in like trying to protect information that were using different networks of computers to send and receive radio waves. And then they realized, hey, we need a way to actually organize this in a clear way. And so if anything, this just tells you the power of abstraction layers. Like if you're a developer, so we're going on a tangent. This matters, and I think I can speak on this as I've done software for a decade now. So abstractions and protocols let you have an agreement with other devs on how stuff works. When you do that, you can build stuff like Facebook, and you can build like autonomous cars and stuff like all the websites you see. It's because there's standards. If you don't have a standard, everyone has to learn the thing over and over again. It's really cool to recognize that the technology for the internet existed since 1969. Like we had Morse code, we had radio waves, we had computers, we had punch cards, we knew how to program. In fact, if I recall correctly, the C programming language, which is it's still used. When did C programming start, right? 78. So it's less than 10 years after this notion of like all the tech for the internet, you could have programmed in C. And before then we had like Fortran, right? Like, there's other languages. 54. Okay, programming languages are not that old, right? So like during the time post World War II, you could be using programming languages. So there was this kind of 20-year period where it was like all the pieces were there, and then everyone was doing it in their own way. Nobody could connect with each other. So imagine you're in, right, I think there's even notes about this, ARPANET. So the internet, originally there was like this OG thing called ARPANET. It was the first public packet switcher computer network. So we defined, I think it was in 1969, right? 53 years ago. There was a different protocol for how to like send data. But then you go, that's the US, right? DARPA, right? That's the US military essentially. You go to England, you go to China, they all have their own protocols. They probably have like, I don't know, let's do it. Like just for the sake to make a point. This might make me look dumb, but let's try it. Early internet let's use a language I know. There we go. So there was a data network called Telecom, basically. I'm not even gonna try to pronounce this. But basically there was early, you can just look up what came before TCP IP in Germany. I'm just picking a country just for the sake of it, because Germany was well involved in World War II, as I'm sure you know.
There are protocol wars. There was a new world war, and it was due to protocols because a bunch of nerds can't agree on stuff. Not as epic as like Normandy or something, but like at least people weren't dying over this. I hope. I want to see just like what were some of the early networks. Point I'm trying to make: everyone around the world had different networks they were using, different ways of communicating, just like we have different languages. The internet was defined as the moment where we collectively agreed on using one format, which is TCP/IP. That's it. Done. Fin. So that's pretty cool. So anyway, that was a tangent. I'll actually write it out like real quick. When was internet defined? When TCP/IP was made. This sounds like an exam question you'd see in like second year university, but like it's the piece of info that's cool, but it's like the least important. It's like, let's just build it. Let's close some of these. So I still want to see like what goes into internet. Welcome Sunflower to the stream. So it seems like routers really encapsulate a big chunk of it. There's this backbone thing, IP addresses. And I know that the way IPs are implemented is there's a clever way, right? Because there's only so many IP addresses you can have. And so I think we had to make IPv6 or like newer versions in order to have a wider range of IP addresses. Actually, I'm pretty sure that's the case. I can check it though. And then IP addresses get turned into funky names. Okay, oh yeah, that's the other part I forgot about was like, where is it? Where did I even write this? Domain registrars. GoDaddy. GoDaddy's not a technical term. GoDaddy is a hosting provider. But I think they're dominant enough with their expensive hosting that it's worth bringing up. Oh yeah, URLs, that's another thing. There's like so many concepts here that I'm just like, I want to at least have 10% understanding on. Oh yeah, there's top level domain names. .com, .net. Yep, some nifty stuff. A DNS, domain name server, that's another one. Oh, geez. Okay, so, all right. I think let's just crank through a couple of these. This is usually IP address for context. Yeah, for those who aren't familiar, every domain is just like an IP address under the hood. Remember we talked about ASCII, maybe if you weren't here in the stream, it was like an hour ago. ASCII just represents zeros and ones into letters. If we go into like what an IP address is, basically every domain name just has an IP address. Like under the hood, it's every domain name, wikipedia.org is a IP address. Actually, let me just like see if I can even prove that. This ping there. So you can see the IP address of Wikipedia, right? You ping it, it actually just has a name behind it, which is pretty nifty. And then you can see we're getting bytes back. Each packet seems like this. I imagine each of these are packets. Each packet 64 bytes. Each byte is 8 bits. We're basically just getting a status response from Wikipedia, but nobody, like, you wouldn't want to go to your browser and have to type 192 or like whatever, blah, 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 blah. That'd be stupid. So we use English, or we use terms we like stuff we're familiar with. So that's an IP address. I'm trying to understand. I think one thing I don't understand is modem versus router. What are these? Okay, I mean that's pretty darn concise if you ask me. Yeah, I mean look at that. Like, you can't ask for a more concise image than that. So you have a bunch of computers in your house, and they connect to a router. All your computers connect to a router. The router is, I guess, a mux, like a multiplexer. Multiplexer is just a device that takes in a bunch of things and outputs one thing. So your router takes in a bunch of internet connections, like from your local devices. It writes them all to a modem, and then the modem connects to the bigger internet. So as it says here, so they can talk to each other without having to do so over the internet. Yeah, but the router basically, so I mean, these are just like, I think this is worthwhile, like kind of understanding these terms. I think not knowing anything about something is kind of dangerous. So I think like meta rant, like I think people either fall on a spectrum where they have to know everything about something or they're willing to know nothing. And I think both of those are silly. And I think like, unless you're doing like surgery, right? Like for most things, if you just spend 5 minutes understanding the bare minimum, you'll have such a better understanding of the global system than like not knowing anything. But I feel like people always have this commitment fear of like, oh, if I start reading about it, then I'll realize how little I know. And then it's like, they don't commit, which is why I'm doing the stream. It's like literally trying to overcome that cognitive bias that I think limits people from doing cool stuff. Anyway, routers, modems. We're not going to do this in the project because, well, we don't need them for the internet. We could just have computer ISP. I think ISP is the next step here, though. We're seeing here in this diagram. So like, let's just go look at like, what is an internet service provider? So I've never understood these actually, like what an ISP is, right? I don't know if anybody else does, right? We all pay internet service providers. They kind of come in, they say, hey, yeah, you're getting roaming charges. And you're like, what does this even mean? Like, why am I paying for this? Like, can't I just build my own, right? I don't know if you ever asked yourself that, but like, seriously. It's like a question I've constantly had. We're gonna answer it right here. This is pretty funky. Okay. So we got phones, we got CD-ROMs, we got televisions. Stuff gets sent to, oh geez, what is going on here? Is this cable? These are probably different networks. Yeah, cable we didn't even talk about. It's a whole other type of network, right? We got Ethernet. Okay, this makes sense. Ethernet we talked about. This is just wires, and this is using electromagnetic waves. This looks like an old, this is an old image because there's no Wi-Fi. Let's find a internet service provider. Let's look up a better diagram. I don't know, I feel like diagram just makes things easier to understand. I don't know why, it's just kind of a bias. Yeah, here we go. Here's this naughty graphic again, where people think that the internet is just this magical thing in the middle of nowhere. It's not. The internet is just waves sending data. Like, no, the internet is a protocol defining how to send waves to and from computers, basically. It's not this random cloud. It's called a cloud because that's a nice term. All the diagrams basically use that. But because, like, how else would you describe this in an image, right? Like, point I'm trying to get at is this picture is wrong. All these pictures of the internet are wrong. And they're wrong for a very logical reason. The reason is because it's hard to explain IP, TCP, and the fact that waves are sent through a bunch of abstractions and protocols that define how to send bytes of data. Like, that's confusing as shit. So like, no wonder they're like just saying it's a cloud. And then business people are like, yay, cloud, more money, more revenue. That's how we get here, folks. That's how we get to this confusing world we live in. It's because of business. Okay, basically I'm trying to figure out like, this internet service provider sounds like this abstract thing, like internet service. Wait, how do internet service providers provide internet? Isn't that a good question? Through a cable, DSL, dial-up, ISP to access servers where they can view web pages. So like, do the internet service providers like download? Do internet service providers download the internet and give it to me? We're getting into dumb question territory. I mean, yeah, this is my first logical thing is your data must pass through your ISP's gateway servers. Okay, so why do internet service providers exist? I'm trying to get at why do these middlemen exist? I imagine it's a pragmatic latency solver. They probably exist because they make it cheaper and faster to have internet because they give you consistency, right? Like the thing we're trying to build, which is just like Raspberry Pis beeping at each other. Like imagine if that's how the internet worked, right? Like that, like you go outside with this Raspberry Pi. Okay, actually, so let's dissect this. First principles. If you're using Raspberry Pi or using any sound or any set of these little things, they can't connect to someone in China, right? Like I have my friend, I got a homie in China. I'm trying to send them a cat picture. There's no way this little board is gonna blast waves to China. And second, if it could, imagine how much wave interference we have because there's say 1 billion people connected to the internet and say the average person's connected to say 1,000 people a day through the internet, we would be bouncing packets 1 billion times 1,000 different ways all through the internet. Like it would just be the amount of wave interference and the fact that like, oh, maybe you have this crappy decentralized device and it's not working. It would really suck. So now we're getting into Web 1, right? We're going from, this is kind of cool. So we're talking about Web 1 to Web 2. So if people are always wondering what Web 3 is, right? Like Web 1 is TCP IP, right? We're just talking about this. Web 2 is realizing that Web 2 is internet service providers and centralized hosting because people realize that it's too expensive and it's too difficult to reliably have internet when everyone's connected to everyone, decentralized, right? Like literally like Bitcoin, Ethereum. And now the whole premise now is that made sense back then. Well, actually, I'm trying to challenge assumptions because I don't know. I'm trying to derive this nomenclature from like what's going on. Like, but basically, I think the part that makes sense here is that Web 2 is realizing that we need internet service providers, and internet service providers, like providers in general, are the reason we're able to like that's where social media came from and was centralized, is because they own all the data. And that means that you just connect to them and then they connect you to everyone else. They become routing agencies. And it's actually kind of fascinating. Like when did the first internet service provider? Let's look this up. First commercial internet service provider, 1985. It was called The World. Right, so let's zoom this out. I think it's worth. I think it'd be naive to not include this in a diagram. I think what's really going on here is we have like Wi-Fi. So we've got an ISP. Internet service provider. Nice. I apologize deeply for my artistic merit. So now see this ISP thing was just up here. We're going to delete that. ISP is actually here. It's connecting. So the computers are connecting to routers, modems. I've abstracted them away. Like there's a bunch of hops needed to get to this internet service provider. The internet service provider just routes data, figures out how to connect you. They're doing stuff with like name servers. They're figuring out the IP addresses. They're mapping them. They're caching them. They're doing all this like funky stuff. I have a vague understanding of how that all works. It's a big rabbit hole. We don't have to go down at this second. We need to understand that basically centralized party owns your data. Like I think this is I'm pointing this out because I think like a lot of people don't understand how the internet works, and one of the things people don't understand is security. And I'm just looking at it and I'm like, well, why do we have centralized hosts? It's because it's too expensive to send data to everyone at once, everything, everywhere, all the time, right? And so we've appointed trusted parties that are commercially interested in hosting and like taking our traffic, routing it to different places. And I think it's just kind of fascinating. Like there's not much more beyond that, but like the first provider was 1985. When did Web 2 start? I wonder when people define this. Yes, the term was introduced in 2004. You know, this is where I would actually step back and be like, I think Web 2 started in 1985, in my opinion. I could post a big Twitter thread, be all controversial, but like if you look at it from just objectively, like what it is, Web 2 is defined as centralizing data and services. That was when the first internet service provider came out, because before then everything was decentralized networks, essentially. Anyway, this is kind of worth understanding that like people have data. It's going through a provider at all times. I think there's this notion of a VPN. This is super funny. If I was like a big Twitch streamer, this is where I would be like, GOAT VPN, and I'd like plug in a sponsorship because this would be like the perfect tie-in. But I'm streaming to like 5 people. Nobody knows who I am. And so I'm not sponsoring anyone, but there they are. It's funny. I just find it hilarious, to be honest. So I'm trying to figure out what a VPN is now, because I think we know enough about the internet that we could quickly answer this question. And I think this is one that's been on my mind a lot. So I want to know, do VPNs use internet service providers? I'm wondering if a VPN is just a decentralized connection. So a VPN is just a proxy. Virtual private network. There we go. So a VPN is probably, yeah. So VPN's here in Switzerland, you're all chilling here, and then like you connect to a VPN, and then the VPN routes your traffic, and then the internet service provider. So basically this whole problem of internet service providers know who you are and what your traffic is. Technically speaking, like I think people need to understand that that is the case, as in if you look at the terms of service for an internet service provider, if you're doing something illegal and the police issue a arrest warrant for you, say they think you're possessing stolen government files, they can reach out to the internet service provider and they can get the internet service provider to provide your traffic and your address. And this is how big FBI busts work. Or this is one way in which big crime busts work. VPNs solve this problem because, or they try to solve the problem, right? They create up a third party, which is like chilling over here, right? Really easy. So say computer one's on VPN. Let's say that they're not doing anything illegal. Let's just say this person, they just love RuneScape. Let's say this person's gold farming on RuneScape. So let's give them something illegal that's not like dark, right? Because this is a positive, good vibe stream. Nothing bad's happening. This person's gold farming on RuneScape. They make a ton of money and they're outsourcing their gold farming to like Venezuela or something. And the government's like, hey, this is like arbitrage. This is economically, you're not allowed to do this. Also, welcome, Ross. And basically they go through a VPN now. The VPN then does the connection to a internet service provider. And then what happens is if the police, I'm using police as the heated example, it could be anything, right? Like if they get hacked, right? But like, let's say police, because that's actually, I think the thing people don't realize is like their search results aren't private. That's the part I'm getting at. Like people assume internet is just like secure, and it's not, for the most part. Like you can have a warrant come through. I've had friends that have dealt with that. So basically if you go through a VPN and the internet service provider gets hit, they're going to backtrack to the VPN. And then what could still happen is your VPN could still be compromised because it's just it sounds like it's just another hosting provider, right? And so I don't know if that's fully correct because I think there's probably a level of decentralization. Like, right, if you go into Onion, right? So basically, like, it's a router, the Onion router. That's what Tor means, right? So if you've ever heard of Tor and people are like, oh, the dark net, oh, there's scary stuff. It's just a network that has a bunch of proxies and encryption. So it's harder to find out where you're coming from. It's not some crazy, it's not some voodoo magic, right? Like, right? People are like, dark net, oh, spooky. Look at that guy's got a hacker. He's got a, oh, Jesus, skulls and crossbones. A deep web, dark web, there's sharks. No, it's proxies. Use TCP. Ha! Look at this. See, okay, like I don't know if people find this as funny as I do. Once you understand how stuff works under the hood, and you're like, "What's the dark web?" It's like, where's that Scooby Doo meme taking off mask? It's like this one, literally this mask. It's just like dark web, TCP/IP, right? It's just the exact same thing. It's the same thing as the internet. This notion of and for context, for those of you who are like, what is the dark web? Like, what is this guy talking about? It's this notion that there's like this underground web full of hackers and illegal activity, which there is, to be clear. It exists. There are illegal activities on the internet, but it's all just encryption and middle party routing. It's not a special internet. And so I think another misconception is people think that like the dark web is this like infamous place where people do like sketchy stuff, right? Like, so you look up darknet and it's like they even use like overlay network and it's like all funky. And so people come here and they're like, ooh, spooky. And the first thing they see are these pictures and they think it's like skulls and crossbones. It's not, it's just TCP IP. We're going to build it. Technically we could build a darknet. We could build our own routing proxy. I just think that's kind of cool. So like, let's just say we got another tangent. The dark web is just TCP IP with proxies, encryption. That's it. It's kind of funny once you write out a list of things and you start Googling, you realize how simple this is. So that's internet service providers. Data centers store data. That's it. I don't think we need to explain what a data center is. Data center does compute stuff. It's not complicated. Well, they are complicated. They're just not a crazy thing. I think the one last thing, basically this stream's turning into just let me understand how this all works so we even know what we're building. And I think that makes sense when you're taking on something huge, spending some time just understanding what it is. Top level domain names.com. Yeah, I think there's a whole segment in here that we're going to want to understand so we got the scope of our project. Again, let's do a quick recap what we're doing for those who are new in the stream. Actually, we got people in here. I'm looking at Twitch. Yeah, we got folks in the stream. It's kind of cool. We're going to build our own hardware that sends data to another hardware device, like Raspberry Pi. And we're going to send like a cat picture or text. And we're going to do this by implementing TCP and IP ourselves in like some programming language. And I'll probably use like boilerplate stuff for like HTTP servers. It's like you get the picture, you know what's going on. And I don't want to have errors trying to translate packets, but like we're going to implement this. We're going to build hardware. We're going to do some cool stuff. So I think it makes it really fun. I think there's something I'll mention briefly here. Domain names, they exist. Domain registrars own domain names. There's like, who determines who owns a domain name, right? There's actually a centralized organization, the International Corporation for Assigned Names and Numbers. This organization owns your domain name. So again, let's revisit this, beat the point home. The internet is centralized. Your freedom on the internet is largely centralized. It is a group of people, primarily older folks, people who have been in the industry for a long, long time, that decide how this stuff works. So like this notion of the internet being all separate and hidden, and like you can hack around and like find people, it's kind of interesting. Like the famous like trope in memes is like, hey, I'm gonna hack you, I'm gonna find your IP. It's like not wrong, right? Like the thing is, you would have to, if you're a government authority, you could actually find where someone lives by backtracking their traffic if it's not all routed. ICANN is what my understanding is like the organization that helps you find your like, it's even got a president. It's got like, it's a full organization. So there is a centralized network, like, right? If we bubble it down here, this diagram doesn't mean anything, but it looks fancy, so it's cool. Basically, centralized parties determine what domain names are available, and then there's a mutual, I think it's called a name server. These big servers basically store records of who owns what, and they map your high-level domain name. What's up? Welcome back. Thank you so much, sir.
Enjoy.
This is the best. Real OG. Basically a bunch of servers around the world that are hosted in like Germany, Switzerland, Canada. There's like a few of them. I think you can call them global name servers. I can't remember what they're called. Maybe it's domain name server? Public DNS. Domain. This is where my knowledge is funky. Going back to Cloudflare. Cloudflare is like our informal sponsor for having good articles. Yeah, so DNS turns your name, like example, into an address. Yeah, everyone on the internet has an address. TLD, there we go. So basically there's these big, it gets really messy in the implementation here. There's a bunch of servers around the world that own mappings, like key value pairs, indicating that this domain maps to this IP address. So it's just centralized, it's just agreed upon. Technically speaking, if you were just like a master hacker, you could just like go in, like you could change this data somehow and you could hijack a domain name, like, because it's just agreed upon by literal people like that manage data centers that have this, and then everyone in the world agrees on it. The reason like the tangent is why crypto is cool is because it's like you have these files, which is the ledger. So like Ethereum or Bitcoin, you have all of your data stored in this public immutable ledger. So like somebody could say, hey, here's all the transactions, you send it to somebody else, they have it, and then you all agree on this thing as it's being passed around. But what's happening is like it's largely becoming centralized too, because if say it's like proof of work where whoever has the most compute power makes the decisions, then people just collect into these like groups of like mining pools that own the compute power, and then they end up being able to make more decisions than say some Joe Blow with a PC in Idaho, right? So there's always this trend of like just basically moving to centralization, it seems, which is kind of neat. Maybe that'll change in the next 10 years. But anyway, that's how domain names work. For the sake of this, I'm not gonna obsess about it too much. We're gonna use IP addresses, so we can add that to our scope. No DNS, no ISP. Again, like we could have an ISP. The novelty of an ISP isn't that interesting. So like, nice. I see the Twitch post. Sin floods like a DDoS. Yeah, basically, I think the novelty still remains TCP/IP. So I think we've accomplished our goal of like understanding roughly like URLs are high level names. They go through domain name registrars, sell them to you, and they work with ICANN, which is this global organization that represents the authority behind domain names, from my understanding. Maybe there's a couple organizations around the world. I bet you China has their own because they have so many proxies and stuff. Like, if I just Google it, China have their own ICANN. Yep. Of course, China is planning to break away from ICANN. Of course they are. This is 2006 though, so we don't know what's happening now. But basically, China does effectively have its own onion network. Like they have their own private network. But there is something interesting here though about, I guess, I don't know if it's a network effect or if it's basically everyone has to use ICANN because everyone else does. So if you don't use ICANN, nobody agrees you own the domain. Like you could say, I own this domain name, but the people that are trying to connect to your computer go through an internet service provider, and that internet service provider doesn't agree with you. And so if you don't have the authority, you're not ICANN, then you can't basically, like nobody's gonna, like you can't just decide what your website is called. You could on a local network, like you could create a local area network and you could have whatever domain name you want and then like hack computers on the local network to believe that. But that's not like, that's why you can't just take a domain name and own it across the world. Like, so on a closed network, you can. Anyway, that's kind of cool. So that's URLs, domain registers, ISPs. And I think we get how packets transition from high level to really low level. So I think we're getting really into the weeds now, down into implementation. Like I think we can safely scope out about 80% or like more, like 90% of the work it takes to make the internet. And then the last piece here is we're zooming in on the OSI model, we're using TCP. Again, I'm trying to say that the internet could be defined as other protocols, right? Like the internet, broadly speaking, is protocols with data transfer. We're using TCP and IP. There's other types. You could have UDP with like whatever, Apple Talk, I don't know. But we're going to be using these two. And so if we scope it out, yeah, I think we're locking in. You can tell you're hitting good scope. So like kind of my meta thing about project scoping is there's typically a period, right, where you're just like reading about random stuff because you're like, I don't know anything, right? Like the first question we asked was, WTF is the internet? That was literally how the stream started. And then we just Google it. And then you just like start writing down, I don't know what any of this means. And then you start creating a word cloud of like what all the stuff is, kind of plot it out. And then it becomes really quick. The internet is this thing. The internet is like this connection. Drew it out. And now it's like, okay, now we can zoom in. Like we've just eliminated stuff. Here's roughly what the scope is. We can still prune it down more, but we can also start getting into like the code section essentially. So now the question is, what part do we build first? And like, now we're getting into like project roadmap. Like, how do we implement it? Maybe we could scope it by trivial versus non-trivial. So how do you make something listen for HTTP calls? I think that's trivial. If it's not to you, I'm not saying you're dumb. I'm just saying that like there's tons of YouTube videos on like how to do this. So it's not as novel to me. How do you use sockets? That's a little bit more novel. Like, it's something that like there aren't a bunch of people talking about it. How do you implement TCP from scratch? That's novel in my opinion. I've never, like, there's like maybe one or two videos on the internet where people talk about this. It's not a very common thing to do from scratch. So this is the crux, implementing protocols, and then hardware, implementing like maybe this is common among electrical eng, but yeah. So I think our scope's gonna be implementing TCP and IP, which is just going to be a huge in the weeds thing of like, what is, because now keep in mind, we know high level what these terms are, but like I have no clue where to start. Like it's not all figured out. I think I've eliminated the stuff that doesn't matter. So like but I want to make sure we're good here. So like, yeah, we're going to implement a low-level driver that sends IP packets to a Raspberry Pi. I think this is kind of like, this is a star, as in it's important. It's not talked about a lot, but it's like, also not the crux. Like it is necessary, critical path. Technically speaking, if we just hard code data in TCP format, we don't do any HTTP, we still have internet. So sockets aren't even a part of it. So we could scope out sockets entirely. Sockets are cool because you can show that data sent throughout processes on a computer is just using files. I actually, full disclosure, I know how to implement sockets, so I don't think it's fair for me to do on stream because the whole premise is I want to do something I actually just don't know how to do. So if I'm going to do sockets, I could do more of a tutorial because I think it's like teach people, whereas the point of this is like just mutually suffer trying to do something. Yeah. Let's see. We're gonna recursively do what we just did, which is we started off being like, how does the internet work? We learned many things. By the way, if anyone has questions, I'll answer in the chat. Like I appreciate comments that have come in. I haven't hit the stage where people are roasting me, but I imagine that happens once you hit like 10 viewers. But we're gonna recursively go in and solve the sub problem now, which is like implement TCP, implement IP, as long as these blocks make sense. So these three pieces. So let's put an abstraction layer here. So we're gonna sub-scope this. Given, I don't know enough about this, let me see. HTTP to TCP packet. Yep, this is what I need to know. So now I know what these things are, but I just don't know how they work. So here we go. Yeah. And then under the hood, HTTP uses TCP to transport it. Doesn't TCP just stand for transport? Transmission control, fine. I think we should, for sake of focus, there's too much noise here, so I'm gonna make a sub page. This is also an ad for Notion, because I love this tool. We're gonna scope this out into here, which is given HTTP payload, convert to TCP IP. That's what we're doing here. So we're moving to like a next phase of this project. We're moving away from talking about in the cloud stuff, pun intended, of like what the internet is, and we're going down into the like, okay, how do we actually take a payload, convert that payload into packet format, implement the TCP protocol, send it to a hardware device. Bunch of stuff going on here. So given, let me first look up if that makes sense. What is an HTTP payload? Let's request types. So HTTP has a bunch of types. I know from doing web dev, there's like post, get, whatever. Let's say we're dealing with post requests because we're gonna send, so basically a get request is mainly built for URLs. So if you go, see in the URL up here, there's a search and then a question mark. The question mark Q indicates it's a get request. And what you can do is you can pass in data to the server. It takes in the URL and then it gives you a response. You're getting something from the server. A post request is like sending a post mail. It's like you're forcing it into the server. And then the server is going to do something. It'll return a status response, but for a post request, you're not typically like returning a payload. Like you're not fetching data from the server. You're just getting like send data, get status. Yeah, I mean, that's the simplest. Get is get, post is to send. Both can return stuff. So I think this is where there's an interesting separation, which is like, okay, people talk about get and post, but like not many people talk about how they're implemented. I think a cool way to do this is just to go to Flask, right? Like, let's just look at the code. Like I think we're getting out of the Google zone and need to just start actually like seeing how people do stuff. Open source is epic because you can do this. Right, so Flask, for context, if you don't use Flask, it's a server, you can define your post or get endpoint, you run it, it just receives data on HTTP, it just sends data through the internet. Great. We're gonna use, actually, I guess we gotta talk about what language we're doing this in. Yeah. So I remember thinking about this. So basically, Golang is really good for the production servers, I found. I'm going to go with Python or C++ because technically they were around when TCP was made. I want to hold myself to a constraint where I don't use software that was around after TCP IP internet providers, like around the 90s basically, because I think otherwise there's too many abstractions and it's hard to actually know how stuff works. But Golang kicks ass, just for the record, this stuff. Flask is in Python, right? So let's just use Python just to make a quick decision. Also to save from syntax overload with C++, to save from compilers, to save from tool chains and all the stuff that causes a headache. So yeah, this is a request, a server request. Basically, there's an HTTP call comes into here. I want to look at an example of a post. Basically, I want to see how it's implemented. That's what I care about. Just go to the source. Just go like a app, I guess. So actually, we're going to start setting up dev environment here to do this. For context, I've just created a new environment. I've got nothing in it yet. The tool set I'm using is I'm using a tool called Brev. Basically spins up a cloud VM for me. So I can define a box. I've created this. It basically just goes to AWS, creates me a computer, and then I can connect to it remotely. So I've created this computer called Internet from Scratch. It's funny, I called it CPP. We're not using CPP, we're not using C++. I goofed you. And it's just because I think there's a lot of headaches that can come from C++ that are not relevant to what we're trying to do. But in reality, if you're trying to build drivers, we might actually just end up having to do like, I'm trying to think about it, but like, yeah, once I get down to writing drivers, it might have to be in C++. I don't even know if you can write a driver in Python, but I assume so. So we will try. Anyway, we've got this project here. Just make a Python file. I assume people can see my code base now. Sick. And let's see if we've got our setup, our tooling working. I want to see if Copilot is working. I've got the completion tool. Oh, and I think we also need Python dev tools, right? So yeah, also this is VS Code. I assume that's intuitive, but if it's not, VS Code. I'm using VS Code on Brev, doing dev on a 32, actually, let me see what we're using. 8 GB, what do we got? DFDU. Oh, I see. So it's df. We got some storage. Yeah, it's cool stuff. Cool. Do you see we got completion now? So I should be able to do something like def add. Whoa, holy shit, that was wild. I didn't even say add. And like it wrote the function before I even thought of it. It probably knows that add is the first thing people think about. That's insane. So there, boom, just implemented a function. If you haven't used Copilot, you should. This tool's insane. But basically, we're gonna import. Let's see what it asks for. Flask. I don't know. That's usually Python's pretty simple. Let's look at a Flask template though. Basically, what I'm doing is I'm using code completion tools to just dig into the repo. It tends to be nicer than going through GitHub. If it doesn't work, we'll use GitHub. But you know, it's from Flask. Okay, let's just set up an MVP. Well, first, actually, let's just do a print. Let's make sure we have a Python environment working. We're gonna use Python 3. We're going to make sure our dev environment works. Can I launch Python from code? Darn right we can. And we're going to do print another statement. We're going to add a debugger. We're just getting stuff set up. Oh, cool. Yep, we got debugging. It's nice and easy. See, with C++, you got to have tool chains and a bunch of, it's just nightmare. I wish it wasn't so difficult. Because I prefer C++ as a language. Okay, so we've got that working. Let's just set up a Flask app. Let's see here. Does this do the thing? I think there's supposed to be like a main function for a Flask app. No module named Flask. Darn right. Pip3 install Flask. I don't have pip yet. Okay. Oh, chat's covering my code. Thank you, sir. How do I move this? Is there like a... Can I change views? I think I can. Ooh, look at that. So we've got these three options. I assume there's like a way to drag this. It's kind of a pain. Entire screen. Sorry, let me just do...
I'd open up the file explorer. We're just going to add a bar, like a draggable thing to your left.
Yeah, File Explorer would do it. Yeah, I assume there's some Twitch Pro gamer moves I need to have to do that, but... Oh, there's pip install. Just follow their installer. I have a bad habit of not listening to simple install instructions, and then it just bites you. Need to install pip. Yeah, we're also using Ubuntu. Just as a heads up. Let's get this. Cool. All right, and now we're going to do pip install flask -u flask. Let's make sure that's right. It's an uppercase package name. It's kind of abstruse. Maybe I can zoom in a little bit too to... Nice. I think that'll do it. Just hiding the stuff that doesn't matter as much. For our viewers with poor eyesight, including me. Just try it. Yeah, so there's supposed to be like an initialize the app and then do like a run command. So there's simple example. Oh yeah, we got to do flask run. I see. Oh, is it because it's an executable? It's not the library. What is this? Let me see. It's usually just a simple pip install. Using pip. So we've done that. Right? That should be installed. Is it uppercase? No. This install flask Python 3. Yeah, let's do the virtual environment path. I think is a good one. Oh, not Windows, come on. What's up, Manuel? Yeah, for context on where we're at, we basically talked a bunch about how internet works, tried to figure all that out. Now we're getting into, like we scoped down to the goal of taking an HTTP payload, converting it into TCP, like implementing TCP under the hood, IP, and then we're going to send it into basically bits that we're going to eventually put on a Raspberry Pi. I think for now we're going to mock it. So it's going to be a lot of just packet conversion and understanding like the core, probably handshake logic of TCP. We'll figure out as we go. And for now I'm setting up like dev environment, trying to get like Python, because we're going to need it. So and we're installing Flask. I do want to make sure I don't brick my machine, so I think it's probably a smart idea to make Python-m. Yeah, it's probably a good idea to like use a virtual environment. I wonder if the problem is the interpreter we're pointing at is different. I bet you it is. 3.8. This is why virtual environment is going to be the way to go, because then we can explicitly create an interpreter for Python and make sure that, because the interpreter is going to determine where our package references work, code completion, debug step through. Yeah. Just kind of jumping back. It's been a while since I've used Python. Let's do this. Got our repo. We're just going to use venv. Should have Python 3, right? Yep. Good stuff. And then I should be able to do, what is the command again? /ven bin activate, I think. Yeah, that's it. So we're activated. Oh, I guess, yeah, I already did it. So this part's interesting. So how Flask works is I haven't used Flask actually in like, I think over a year. So I'm trying to just recall how this application runs. It's not a library. I thought it was a library. Like Fiber and Golang, Sanic, like they're all like simple package installs, and then this is like let's just follow the instructions for now. Just keep it simple. Bad tendency to derail and be like, I must know how it's coded. It's like, no, it doesn't matter. Okay, we're gonna check the version. Well, that seems like it installed. Getting good signs, good vibes from Flask. Yeah, so pro gamer move for everyone. Use virtual environments. That's the takeaway. Don't not use a virtual environment. That's dumb. Because you'll brick your environment, then you'll have package issues, and like you won't know how to fix them. It's a nightmare. It sucks. Versus when you have Venv, you can just like delete your environment. I think we've got what we need. Is this different? Looks like the exact same thing. So what do we got here? Could not resolved. So we have an import thing going on. Oh, I bet you it's because VS Code needs to now point to the new interpreter. So let's find it. We have Venv now. Bin. Is it in here? It's probably in here. Python 3. Is that how it works? Hey-oh. Look at that. Isn't that sick? Okay, so now basically all that was so we can do, I'm using a NeoVim, Vim key mappings in VS Code. I went down the whole path of like being pure Vim, and then I found that like having nice tooling is also nice. So, and like not getting stuck on Vim setup. Also, if I'm a bit slow, I migrated from my Linux laptop to Mac because I can't Twitch stream on Linux. Like my whole Twitch stream would have been Twitch setup drivers episode 1, not anything else because so many drivers don't work. But anyway, we've gotten to here now. We've got NeoVim, which lets us use GD to go to definition. So I can just I should be able to just jump recursively really deep into the code, right? Yeah, look at this. His instance, you can go right down into like the fundamental like type definitions and like look at this. Isn't that, I know that's sick. Like, and then if you want to go back, it's I have a key mapping for Control O, so you can just go back. I think it's pretty darn cool if you ask me, being able to jump into stuff. Anyway, now what this lets us do is better than GitHub in my opinion. I don't know why GitHub doesn't do this, but first example, we're gonna put some code. Post endpoint. There should just be a methods equal post. Yeah. And now we should have Copilot do this for us. So it should just be, look at that. Sick. If you're not using Copilot, use Copilot. Look at, I didn't even type anything. It's just like, bam, post. That's it. And now we can start going into the route function. We can understand how post is implemented. So for context, all this I'm doing is to understand how an HTTP payload is captured in Flask. Basically, like it's just a bit of a programmatic way to dig in and see that this is all these web apps, like all these web servers are doing, is just taking in blocks. And then I know somewhere we can have if I go Google, I'll find a payload that describes what a post request looks like. But that's not as fun. I think going through the code and finding how the code does it adds a bit more color to programming. So we got a decorator. Let's see here. So we've got something like a method. Pop endpoint add URL rule. Yep. So we got a decorator. Okay, so how does this work? So they're funky because they use decorators. So we got methods app.route / So this is going to decorate the function and do a post request, which will, method route post. So in the case where it is a post, it's going to call this function, pass the payload, go into here, route method equal method. So now there's a general route function. Now we're back into this. Let's go down into it. URL rule. They're not going to let me go deeper into the code. I would love to. Yeah, it's typing. We've got 2 places where we have post in here. Might not let us go deep because they're using decorators. Being all funky. But we will find a way. There we go. There we go, there we go, dispatcher. So yeah, if you implement a get method, it'll handle get requests. So there's gonna be a dispatcher in here that handles post, right? There's probably a post request function hidden in here somewhere. Let's try going it through this way. Views, we've got scaffold. So I think there's something it's doing in Python that I'm not familiar with, which is how it like routes there. Is it pop? Pop's just a queuing operation, or a stack. So that's nothing funky. Let's see. Okay, let's go. Let's actually revert. I thought this was going to be easier. So let's use a hybrid of Git. Yeah. We're going to Git. We're looking for post, the thing that implements the post request. Yep. Yep. There's not too many code parts, so this actually looks accessible. So this is using Rust? Nifty. Basically, we got to figure out what wizardry they're doing to actually like take a post request and then process it, because it's hidden around so many things. I'm trying to figure out this not implemented error. As view, I think it's just because they're doing polymorphism somewhere, a bunch of class inheritance, and one of the subclasses implements the post, and we're not seeing which one it is. There it is, frozen set. Interesting. Just gonna open a few of these. This looks promising. Just good old Google. This is too high level. I think we're getting into the dark unknown where people don't explain how to do stuff. So we're just gonna have to like, this is kind of how it gets. I think the other hypothesis is a post request is just a payload and there's actually no difference. Like it might just be like such a simple function that it's like, yeah, we're here. This is error handler. I wonder if it's doing a dynamic, like if the underlying handlers it's using to handle a post request is different than Flask. Like is Flask not doing it? Which is kind of interesting to me. Yeah, so we've got main, post. There we go. Pre-process. I think we found what we're looking for. Full dispatch request. So this is getting called from a decorator, by the looks of it. There we go. And what is pre-processing doing? URL funk, ensure sync. See what all this is. Yeah, okay, so still Flask stuff. Dispatch. This seems like where it has to be. Yeah, matches the URL, returns the return value. Ensure sync. Send, yeah. Finalize request. There we go. Yeah, now we're dealing with headers. So, okay. So this is where they're handling response, at least. Okay. So this is the crux of how they're handling a request, any request. That makes me ask the question of HTTP standard get versus post. Let's go to HTTP 2. Yeah, we're doing HTTP 2 because HTTP 1 is long deprecated. And now we're getting into the crux of it. Let's just see how post is done. Yep. I'm wondering if all those HTTP2 encode. I'm curious if get and post are actually just the same thing. Because so typically when you go down a rabbit hole and you're like, I can't find the code for this, and then you realize that it's all an illusion and it's just like an abstraction. It happens so frequently. Cool. Okay, so yeah, this is like what I mean. So what we're trying to understand here is how HTTP takes a call and then how that turns into a TCP frame. And maybe we can confirm just a TCP packet. Is there a standard format? Yeah, so we've got this image we looked at before. TCP packet header. Yep. So the interface we're trying to connect in is HTTP to TCP. That's what we're trying to grok right now. I want to see in the weeds what's happening to the code to go from HTTP to TCP. So this is cool. Yeah, this is exactly what I thought. So the reason we can't find a handler that does post versus get is because their request format is the same. Like they have the exact same data, and then the only difference is in their post processing by the looks of it. So but these are both get. I want to see a post because like they must be different. You and me both, homie. This guy's also trying to understand HTTP 2 in detail. Classic Stack Overflow response. You're wrong. Okay, so an HTTP request is it's a header, a data with a stream ID. What I'm trying to figure out is if it comes in a chain, because I want to assume we're processing like just a single request. I don't want to do like streaming data because that just adds a level of complexity in the application level. Yeah, and then there's multiplexing and like different frames interweave. Nope. I mean, this seems like the best place to go. This is it. 2070, what? When did this come out? 2015. That's pretty recent. Yeah, I mean, for context, this site has all the OG proposals. Like it's got IP, it's got TCP. We should actually probably find the TCP and IP ones. I have a feeling this is going to be a ground truth we are at for a while. So here's TCP. It's named after a proposal. Original. There it is. I knew I had this. Is this TCP though? Because I think there's the one I'm looking for is 83. We'll find it in a sec. This seems like the proposal of it, and then the actual design's different. This might be it. 83? 81? Yeah, this seems like the OG DARPA internet program. Functional header format. Yep, I think this is it. I'm starting to become familiar with this format. It's the source, destination, where's the checksum? Yep. There's these things we don't know, but this checks out from what was shown on Wikipedia, so I think this is a good baseline. So an HTTP request has to turn into this. That's the first thing, right? And the question I'd have is it one-to-one? Is it one-to-many? I imagine it's one-to-many. Like, we can look at this. I mean, here's all the details. Let's just read it. Window, checksum. It's just a bunch of config. There's the states. Yeah. So TCP also handles this notion of the three-way handshake, right? Which means we'll have to implement that. And that's cool because it's like, the three-way handshake is across two devices, by the way. So let's put that in here. So I don't know here. This is I'm just gonna put this in red. I don't actually know if this is one-to-one. It's got to be one-to-many. I just don't know the encoding. But basically, we have these three parts. We have these three chunks we have to complete. I'm trying to think if there's a way we can like partition it into one end-to-end piece to get it all working. So, for example, there's going to be a handshake process, which is like take data in. We need to still send just a dummy request. So like TCP three-way handshake. What I'm getting at is before the payload is sent, the payload encoding is like the thing you do after you establish the handshake. Right? We still got to do this. The SYN and the ACK part, like the handshake is like core TCP, which we could do first, right? Like this other part is kind of like just end work. It's hard when you're in the middle of working on something, but it's really important to be like, what actually is the thing here that's the crux, and like what else can we just like push to the side for a sec? So we don't go down a rabbit hole and like spend a whole day coding something that turns HTTP to TCP. Like that's not the crux. What we really need is like the handshake. Then we need to send any data. We could send anything. It doesn't have to be a cat yet. We want to get there. So it's kind of like if we break this into milestones, we know what we need to have. Milestone 1 is like, or like the bare minimum is we're going to establish TCP handshake with mock server on same machine. Establish TCP handshake, basically. And then it's going to be milestone 2, TCP handshake across a Raspberry Pi. So the first step we're doing is just getting the handshake right, send dummy bits, and we're going to send just garbage, but we're going to send data. Like we're going to do the thing where it's like a bit has been transferred to the same machine. Then we're going to add the Raspberry Pi, which I consider a very scoped thing for hardware. And milestone 3 is mod payload to be cat. I think you might not think this is important, but I think this is important, that we send a cat picture as soon as possible. It's our project requirements. And as the key and only stakeholder of this project, I think it matters. So, so 4+ is like HTTP server. So then what we're going to do is So we're scoping it further. We're going to end up getting from HTTP server, encoding it down into a cat, doing the handshake, sending it across a Raspberry Pi. But for now, we're just going to start. We're basically doing bottom up, just to be clear. So we started top down. In here, we went like, here's Flask. How do we just start coding these interfaces? But I've realized since I don't know how these things are implemented, starting top down is really dumb, because what's going to happen is we'll code a bit. We're going to realize, oh, the underlying thing's different than I thought. And then it's going to break all the higher level abstractions. So it's just like building a house of cards by starting at the top. That won't work. So we're going to go right down to the bottom. I think hardware is a safe point. And I think on top of that, we should be working directly in the TCP level, saying, how do we define the packets? How do we define a handshake in like Python or C? Put that down there. So we'll hold off this question until we're at here. HTTP to TCP is a separate thing. We don't have to care about that the second. Let's zoom in on, handshake. So there's this thing about syn and ACK. I don't know what this is. Cool. So there's this syn. What is syn and ACK? Can somebody just define this? Syn, synac, ACK. I don't want featured snippets. It's just gonna be ads. I don't want like PC Magazine explaining this. Let's try this one. This is actually decent. There's the ads I told you about. Can we actually just like block ads entirely? I already have ad blocker running. It's no longer working on ads. These are sad times when it runs. It is the responsibility of the client to make the initial request to start the connection. So there's control bits in the protocol header to facilitate this request to connect. We'll need the syn flag, the ACK flag. So when a connection needs to occur, so the server's just chilling. It's always listening. That's kind of cool. So it's going to be a microphone. And then the connection has flags, and that's the control bit. Where does the syn flag? 1000. ACK. Yeah. So where is this thing? Sequence number. I need the actual breakdown of how many bits are in each part here. It's probably going to be in the original OG specification, right? says it's 1 bit. Yeah, 1 sequence number used as the indication of a connection. Okay, it's gnarly. There's a bunch of extra logic. There. So this makes sense. So let's just understand at a high level, like how the shake works, and then we'll understand the packets. Because it sounds like that's the minimum thing we need to actually send this, is we need to know how the packets change in each request. So we send this, there's a flag set. First sequence number should be for the rest. This initial packet allows the client to set what the first sequence number should be for request packets originating from this client. Okay, so the client's kind of saying like, yo, I got a request, here's the bits that represent this request ID. Then the server responds with an ACK, like an acknowledge. It acknowledges the SYN, the synchronized or whatever, SYN flag and the ACK bit, confirms the sequence number, and then it also sends back the first sequence number should be for response packets originating from the server. Okay. So why is it 3-way handshake? Why not just 2-way? Why doesn't ISP use a 3-way handshake? Oh, I see. Duplex, so it's bidirectional communication. Oh, I see. So it's responding and creating its own connection. So it's like, so if you go into this milestone, so there's SYN ACK, send request from client to server. So basically the server is always listening, but it doesn't have to do anything with the request. It needs to like acknowledge that the request is something valid. Because you could probably like almost like the equivalent of a DDoS server by just sending garbled signals. I see. And then SYN-ACK is server says it's cool to connect, also asks to connect to client. So it's bidirectional. Duplex. Let's just make sure duplex is actually the name and I'm just being dumb. Network. Duplex just means 2 directions, right? Yeah, it just means two threads of communication, so it can listen and send at the same time. Technically speaking, if I'm building if I'm doing this using beeping, like a Morse code, it can't send and receive at the same time. Like that's not the nature of how this works. Because like it would affect itself. There might be interference. I think that's going to be a hardware thing. We'll figure that out. Separate problem. that's getting into like the actual like signal problem is like it can't, how does it send a request and then not interfere with itself? That seems like signal processing. It's probably not a blocker for implementing a web app. Like we'll work around it. We'll probably send 2 different signal types. Anyway, way down the road. So simple enough. Send a response back saying acknowledged and I need a connection, and then this server responds to the SYN-ACK packet with an ACK packet that acknowledges the server's sequence number request. At this point, the through handshake is complete. Numbering, connection is up. Okay, cool. Nice. Let me clarify my understanding of this actually. Okay, so these words make it sound confusing, but it's just basically, wait, do they have the definition here? Synchronize, acknowledge, okay. So it really is that simple. So request, get a response, also request, say server is chill to connect with client. That's it. There's some packets being sent. That's the logistics of it. We can do this in Python by creating mock SYN-ACK servers. So we can do, let's do it here. Okay, so we got a server, we got a client. They need to send each other messages, basically, in some way, right? So I'm trying to think of how that process looks. So how's the control flow going to look like? So client sends SYN request to server. The server responds with SYN-ACK. Actually, the cool thing here is there's no such thing as a response now. The servers are just literally sending data to each other. So they're both listening for stuff. So like this notion of sending and responding isn't the case. They're always listening, and they're just listening for some sort of data, and then they process it. So we need to we're working in 2 levels of abstraction here. One of them is thinking of sending and receiving, but that's no longer how this works. So this client server is on the Raspberry Pi is gonna make a beep sound. The server will be listening. The server is gonna broadcast something. So let's just call it broadcasting. Server broadcasts a SYN-ACK. Yeah, so I'm gonna, just to be clear, I'm gonna redefine send and receive with broadcast, because that's all that's happening is they're broadcasts. SYN request to server. Server is listening for SYN request, processes it. The server is going to then broadcast a SYN-ACK message. I'm removing a request entirely. I'm saying it's broadcasting messages. Listening for SYN, processes it, receives and processes. The server then broadcasts a SYN-ACK message. The client is listening for SYN-ACK message. So I'm designing this in a way where it's technically not as bidirectional as you'd want in TCP, where the client could also be the server. I'm like, no, the server is the server, the client's the client. I'm building it down in the TCP level, but technically speaking, if you were building this for a production setting, you would want to have both of the server and the client be able to respond to ACK or a SYN request. Should be able to go both ways. I just don't want to deal with that right now. That's just a headache. What we are going to do though is we're going to set up a mock environment where we're going to come up with the packet encoding. We're going to send it in Python land, like user space, and kind of get what we want going. And then we will work on the second problem, which is encoding it down to the bit level for like sending it over hardware, which I think is the cool hacking part. So client listens for syntax, receives, processes it. Client broadcasts ACK to server. Server is listening for ACK, receives, processes it, and then client broadcasts payload. Server is listening for payload, receives, processes it. That's it. How do we code this? So functions in Python aren't stateful. So we need a state machine. We need a level of state in this. Can do it using structs. Like I could just define a global variable, but it just pains me to do that. Technically speaking, we need a global variable regardless. If we wanted to do this really cool, we could use sockets. We don't need to do that. It's too verbose right now. Actually, Python just has global variables you can define in a function, right? I don't think we need to worry too much about the programming practices here, but this isn't a good practice, just to be clear. Just read about it a little bit. I think you're supposed to define like global in the scope of the function or something. Yeah. Let's look at this. Does this work both ways? I get the examples. How are global variables implemented in Python? Come on, guys. I want to know how global variables work. They keep giving me these like, this is how they work, and then they give me like examples. I'm like, no. That's not what I mean. Okay, well, I imagine Python does stuff with, what language is Python built with? C Python. C Python probably has registers, and it probably does stuff like C extern. I bet you that's how global's done. Anyway, I don't think this matters at the moment, but I'm always curious how global is implemented. Like, so Python's using CPython, which is the version I'm probably using for Python 3, is using C, and C uses extern to have global state. And so that's probably what this is. It's probably just like writing extern. Anyway, I don't think it matters for our case. We'll do this. It's editable in both places. It's doing the job. State. Cool. They're going to have a state, and then what is the state? Well, a state could be I mean, we're just building a state machine now. That's all that's going on. I mean, this is like traditional software interview. We could just think, how do we want to do a state machine? I'm just trying not to make it too verbose. So the client is going to have right? The client's going to have waiting for syn. That's a state. The client is going to have waiting for syn ack. The client is then going to have, well, then the client's just going to broadcast ack. There's only a couple things here. So the client is waiting for a, broadcast the syn. There's a starting state. We're going to broadcast. Then it's going to enter the waiting for syn ack state. That's it. Once it hits this state, it's going to, there's only a couple states then. So it's going to receive the syn ack, and then the client is going to broadcast the result, and it's just going to go back to starting state, like a refresh. Nice and simple. And then I imagine it'll stay in this state for a while, typically, if we're sending a larger payload. That's the only difference. Cool. Seeing if any of the Discord homies reached out. All right. And then server. And so how do we store this state, right? Like this is pretty, I like the idea of encoding the state types. So it's like, I mean, we can just keep it super simple though right now. It doesn't have to be clean. So on the client, we're basically saying, and do we want this to run like a control loop every time? I think we do, right? Because like, what's the ultimate demo going to look like? It's going to be, we're going to have a for loop, like a ticker. Well, no, actually, technically speaking, the global implementation will be there's a separate listener that's always running. And the moment a request comes in, it gets hit. So the listener is a separate thing. Then there's going to be this like loop. There's basically an action loop because Python has a global interpreter lock. So you have to just run this. Like you can't have a bunch of multi-thread, multi-processes. They're not actually running concurrently or in parallel. So do that. And we're going to call like a, I don't know, if state equals start. And I'll use a, yeah. I mean, this is definitely going to be a class. This is going to be classes. If state equals start, do start. If state equals wait syn ack. Yeah. I'm trying to think if there's a cleaner way, because we're going to have this while loop that's just going to, like, ultimately, if we're listening to both, how's that going to work? Can Python do that? Because I think we can do this using files. Okay, basically, what we can do to hack around using sockets is basically there's going to be a driver. There's going to be a Python driver, we'll call it, that is going to listen. It's going to check the hardware at some point once we're connected to it. It's going to receive data on the hardware, process it, realize we're at the next state. It's going to set a file. And then what's going to happen in the global state is we're going to constantly check. So we're going to be like, check local file, check local file for inbound payload. So like we have a listener essentially. The listener is going to be constantly just looking at if there's a payload, and if there is, like which we can do right here, just like do a check. Is there a local payload? And then if there is, broadcast a SYN. So now we're moving away from having it all down here. Maybe we can keep this, put it in Notion. Yeah. I think this is clean. Let's just remove it. Now we're waiting for synac, and then check local file for synac payload. Hack. And then state equals because now we've established like a publishing permission, so we can just send data like directly to the server now. We don't have to think. I actually don't know how the TCP closing works. I need to check that. Three-way handshake, yeah. So we've done the handshake. I get that, but then what happens after it's open? How does TCP handshake close? You send a FIN packet, and then you wait for a FIN response. So there is a connection close area. I don't think we have to care about it right now, but it's worth noting that that's a thing. There's a sending state, let's just call it. If state equals sending. Now what are we gonna do? Broadcast payload. I'm just gonna put a sleep. Yeah, we're gonna sleep a bit just to make sure that the server's ready. Whereas in reality, there's gonna be like retry logic and all that. We don't need to worry about all that, because again, part of the requirement here is we don't care if some packets get lost. We just want to send data right now. We'll return, and then we'll do return. Return. I mean, this can obviously be bundled up into like a dictionary and like simplified into like a very simple call. I don't care. Just keep it simple. Yeah, I mean, sending, it'll broadcast, and the state's going to be start. We're going to go right back to start. Or actually, we can just to make sure data gets sent, let's just keep the state in sending mode. So once it enters sending mode, we're just going to DDoS the server, basically. We're going to make sure it receives these packets. But we'll have to add a decent timer, and that'll be the implicit retry. Okay, server. Start. Check local files for inbound payload. If what is it? If SYN found is false, if syn found. The state. Okay, so if we find the payload, we're going to broadcast synac. Wow, look, it knew exactly what I was going to do. That's cool. And then we're going to wait for ac. That's the next state. Let me say if state equals wait ac. Same thing. Ac payload. Then ac found is false. If ac found. I think that's how it works, right? It's sanity check. Yeah. I think I got like a ping. Nice. Cool. Syn, respond to synac. Now it's waiting for an ac. Yeah, it does its broadcast. And now it says if there's an ac found, nice. Openly listen for packets. And now we're gonna do state equals listen. All right, we'll just say receiving. Yeah, and then this one is sending. Cool. So we have the handshake. We'll enter a receiving state, and then we'll do a final state here. If state equals receiving. Oh geez, fancy. For inbound packet payload. Yeah, that's it. We should move the return here. We should always be bailing. Again, ugly state machine. It doesn't have to be nice right now. Cool. And now we can have a loop where we do while true. We can run these technically at the same time. It's not the biggest deal. Yeah, I think running them at the same time is kind of cool. There shouldn't be a race condition here because they're not receiving or sending the same thing. They're not trying to manipulate data at the same time. So it's always going to be lockstep. It's always going to be at least a couple ticks before the handshake is complete. And I like it being in one tick so that, well, there'll be a race condition where sometimes it'll be less ticks because if we, well, depending on, actually, no, since the ordering of these will always be server first, it'll be predictable. If we ran these as sub-processes and they're always just ticking, then it'll be kind of unknown. But thankfully, Python's very strict with this. So let's sleep. Oh, cool. And so let's think here what we want for the next part of this. I think getting a handshake pretty well set in, like, getting the handshake logic working is nice. Using the actual packet format, I think we should be doing that. And then the actual logistics of the broadcast will partition into a separate part. So for actually the driver logic. For now, we'll just focus on like send receive logistics. Because I think that'll give us most of the understanding we need without going down too many rabbit holes. see here. Sleep. So the payload. This is just going to be bits, I think. I mean, we could, yeah, I mean, I think we ought to do this as bits if we're trying to do a real encoding. And what that means is we can't just, we can't go in here and just type ones and zeros. The reason is because these ones and zeros are actually ASCII. So each of the ones and zeros is like an 8-bit character of some sort. It's either the 8-bit string representing the 1 or the 8-bit string representing the 0. So if we encode it like this, it's going to take a lot of space. It will take, I think, 8 times more space than we anticipate, and decoding will be really confusing. So what we want to look at here is and I mean, technically speaking, we could skip around that. We could just do a, what is it? We could just send ASCII, but once you send that down to a driver, that's gonna suck. Basically, like at some point you got to work with bits. So Python. How do you do bit strings in Python? Then we got to learn how to do bit string hacking in Python. So there's bit strings, bit streams. Just trying to understand the difference. Nice, that looks like what we want. Yep. Is there a way to go from binary to the, can I just write a stream? Nice. Does Python have like a native way to do this? Python 3 bits. There must be. There's like bit logical operators. We don't need all this like libraries. But I mean, I want to use them if there are nice libraries. Yeah. So we got our base 2 conversion. what is Python a 32-bit or a 64-bit? Or actually, no, the real question is TCP... They spelled format wrong. Official military document, they spelled format wrong. It's funny. I'm telling you, this is like one of the most important documents. Okay, so it seems like this is like 64 in total. Looks like it. 16, 32. Seems like more. Seems like 400 something. How many bits are in TCP packet? I just wanted a quick answer, but no. I see. So this means it's 30, 10, 20, 30. So 32. Yeah. So this is 30. This implies 32. 32. I see. And then you can read all these blocks. So there's like 32, 32, 32, 32, 32, 32, 32. 1, 2, 3, 4, 5, 6, 7. 7 times 32. So there's thought it'd be 8. Or no, 8 times 32. That makes sense. My gut is it's 256. 7. Yeah. So there's like up to like 256 bits. And then what we got to do is effectively create we got to do some bit string hacking, and we have to be able to set individually all these fields that we want in order to break it down. But I think we also need to understand the connection between TCP and IP to do this. Cool. And I think we're also still at a level where we need to understand a bunch more about how like IP is implemented on a system. Like it's going to be file reads, right? Like I get that, but are there more aspects to this we need to get? I think for now though, we're at a pretty good milestone. I think we're at 4 hours, so I'm at my logical cutoff. But what I'm going to do is post a video like how far we've got so far, and then sometime we will continue on the next chunk, which, yeah, the next steps are going to be bit conversions to represent TCP packets. Then we're going to do a conversion from TCP to IP. I think the next stream, the logical point would be break down all the packet conversion logic, all the Python level libraries, get ready so that the next step is purely hardware. And then we'll do like a hardware hacking session. But cool. I mean, thanks for those who dropped by and are still chilling in the chat. I'll post this and answer any questions folks may have, but hopefully you had some fun.